3/8 CRT. Welcome, Dato Yusof. Good morning to you.
Morning, Prof.
Yeah, good morning to you. Thank you for joining. Kita ada another 5 minutes. I hope today is good. Today is good for you.
Yes.
Okay. Kita will have a 10 o'clock the short speech by the TNC.
Yeah.
And then you will take over. You can talk how long you want.
Just a short one.
Okay. Then we have our partners from international partners too.
Sure.
Professor Ken Grattan will take over. Okay. So you are at your office or at home?
At home today, yes.
At home, huh?
Yes.
Okay. But your home and office very near, kan? Just dekat.
About 10 minutes away.
Very convenient, lah. Very convenient. Okay, okay. I think give them about 2-3 minutes. Okay.
All right. Okay.
All right. Okay. Okay. I will see you shortly. Good morning, Professor Noor Sada.
Morning, Prof. Harris.
Okay, we give about 1 more minute, huh? 1 minute.
Okay.
Because we have about 200 people registered. So far, we have 42. We have 100 people registered and 123 from DPKL, quite a large number from the Dewan Bandaraya Kuala Lumpur. So we have about 200 over because Google Meet allow us to only allow 100 people. So the rest we go simultaneously using YouTube.
Yeah.
So they can listen through YouTube. So in 1 minute we can start. We hope Professor Ken Grattan. After your talk will be Dato Muhammad Yusof, the CEO of MIC. I think we are very happy to have him because he's the person that fund the. Good morning, Professor Ken Grattan. It's 3 o'clock in the morning. My sincere apology. I think you might not have gone to bed yet. Okay, so we have just to introduce. We have the TNC Deputy Vice Chancellor of our Research and Innovation, and we also have Datuk Muhammad Yusof, our Chief Executive Officer of MIGHT. MIGHT stands for Malaysian Industry Government Group for High Technology. So the Newton Fund is our host in this country is MIGHT actually. All right, so we have the CEO. We hope the CEO can capture something what we have done. So we hope that in future we can get more funding from MIGHT. Hopefully lah. Hopefully we can get more funding from MIGHT. Okay, just to share with all the members, now it's 10 o'clock. So I would like to invite the Deputy Vice Chancellor of University of Malaya, Professor Noor Saada, to give about 10-minute welcome or just to say something about the conference. I will pass this thing to you, Madam.
Thank you, Prof. Harith. Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to all our distinguished presenters, participants, and guests. On behalf of the University of Malaya, I would like to welcome everyone to the 2021 International Conference on Innovative Optical Sensors. I would also especially like to welcome our guest, Dr. Muhammad Yusuf Sulaiman, the CEO of MIGHT, and our partners from the City University of London, Professor Ken Gretton, Professor Azizur Rahman, Professor Gilberto Brambilla from Optoelectronic Research Centre, University of Southampton, and Professor Luigi Seni, our guest from the University of Campania Luigi Vanvitelli, Naples in Italy. This conference is jointly organized virtually by the University of Malaya, City University of London, and the University of Southampton. It is part of the Innovative Distributed Sensor for Landslide Detection project, which is sponsored by MIGHT and the British Council through the Newton-Ungku Omar Fund. I would like to take this opportunity to express our gratitude to MIGHT for funding this project, and I'm confident that Prof. Harith and his team are able to deliver the project's objective successfully. I was also informed earlier by the organizing committee that about 232 participants have registered to attend this conference. This is a big number, and they are not only from the scientific community, but also from the public. This number is more than what was planned earlier. Thus, this conference was also broadcasted live to the larger audience through the PRCUM's YouTube channel. I hope that this conference will be able to deliver and achieve its objective in providing an effective forum for all researchers to share their knowledge and findings with the public. As this conference is open to the public without any fees, we hope it can be an initiative opportunity for us to reach the public on importance of scientific research and how findings can benefit and change their lives. I believe most scientists and researchers know that their work are filled with technical terms and complicated ideas and concepts of ideas, but I hope the presenters will be able to make their presentation much easier for the public to actually understand and communicate their output with the public. Finally, I would like to congratulate the organizing committee and our partners in UK who have directly and indirectly supported this success and the success of this conference despite all the challenges that we face due to the pandemic today. I wish you a very productive conference and a very exciting and encouraging discussion. May Allah bless us all with good health and make this event a successful one. Stay safe and thank you very much.
Thank you so much, Professor Noor Saada, for the kind speech. I think we go next to Datuk Muhammad Yusuf Sulaiman from the CEO of MIGHT. I think a very important guest to us. You would like to say something, Datuk? I think your mic is muted, Datuk.
Still muted, yeah? Yep. That's always the problem with this online. So, Bismillahirrahmanirrahim. Very good morning. Assalamualaikum warahmatullahi wabarakatuh to all participants in this conference. First, let me recognize Professor Dr. Noor Saada Abdul Rahman, Deputy Vice Chancellor R&D of Universiti of Malaya. Distinguished Professor Dr. Harith Ahmad, and thank you for your kind invitation for me to say a few words here. Professor Kenneth Grattan, and other Newton Fund Impact Scheme project partners from UK, and ladies and gentlemen. Well, since I'm from MIT, I'll just like to say a few words about the Newton-Ungku Fund itself. It is the largest bilateral STI program between UK and Malaysia. So to date, it has facilitated 28 programs since 2016 based on three main pillars: people, strategic research, and translation. And yes, Dr. Haris, you can always come back and ask for more if you have good proposals.
Thank you very much.
So we like to invite others to also come. To ensure an impactful delivery and continuity of the Newton-Ungku Fund projects, which were funded and facilitated, the British Council, UK Research and Innovation, or UKRI, and MIT decided to launch the Newton Fund Impact Scheme, a new scheme in 2019. So this scheme provides further funding for current and previously funded NUOF recipients with the aim of maximizing the impact. So 14 projects are currently being facilitated under the NFIS, the Newton Fund Impact Scheme, including the innovative landslide detection using advanced distributed optical sensors, which we are talking about today, a project by Universiti Malaya and the City of London University. So congratulations, Dr. Haris, and also those from City of London University. Now,
Okay.
as I believe this project is built on the success from the previous institutional links projects and its strong partnership between the team members. The project will enable the lab-scale sensor system for landslide prediction, which was produced in the previous project, to be field-ready and to be deployed at site. We believe it will benefit the relevant stakeholders, including the city councils and the local communities, through better, earlier prediction and warnings of potential landslips, with lives safe and expensive damage prevented. I think this is very awesome. We look forward to facilitate more good and impactful projects under the NUOF program. We at MIT have also started new bilateral programs with other countries like Turkey and Spain, based on the same match funding approach. So with the NUOF experience, we are expanding the countries that we are partnering with. The benefit of the match funding model is each partner will contribute only 50%, and you get the actual R&D outcome at the end of the day. So I think this is a very good arrangement. Process is very transparent and very objective. That's why we have so much proposals compared to other programs. So we believe bilateral and even multilateral collaboration will allow collaborating countries to bring the best minds together and produce internationally recognized innovative solutions to either address global issues or to penetrate a greater market. So on behalf of MIT and the British Council, I wish all of you best in delivering the online conference. With the global pandemic challenges, virtual engagements are becoming normal and crucial to any collaboration, especially which involves international partners like today. So I wish I've met Dr. Haris in person and the rest of you, but this is the way life is now. But I hope it will not compromise the quality of deliverables and impact of the project. So again, congratulations to everybody involved in this project and all the best for the next stage. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam, Dato'. Thank you so much for the kind speech, Dato'. I'm so delighted. Just to share with you, we have made very good progress. I think the bilateral project is very interesting. Sharing of ideas, we have good contribution from our international partners like Professor Ken, Azizo, and Jibato. Sharing of ideas, we have already published about four papers in Q1, and hopefully in near future we should do a bit more. And just to share with you, last 2 days I got an email from OSTI. We did apply for one grant on the landslide, because landslide is very important due to the climate change, right? You get flood, you get everything, so we should prepare ourselves for the eventuality, not to get caught like COVID-19. All right, we have to prepare ourselves. So it's a short notice, but we have to present our defense on tomorrow afternoon. So hopefully we can get. Then from then on, I think we should be able to go to the market. Should be able to put the thing in the market. Just share with you, Dato'. Thank you very much for your funding. We are so grateful to you. I am extremely grateful to Mike, a very good organization. So I think not to spend more time because we have to maintain our time. We would like to invite Professor Ken Grattan. He was the former dean of postgraduate study. He's a very distinguished person in sensor, actually, very distinguished person. He is a chief editor of measurement journal. I think a very well-rounded, and he has many projects with British Rail Tube to look at to implement sensor into to detect. You know, if you look at the rail, they use electricity just to detect the behavior to make sure there is no damage to the line and so on. So he has major project. I would like to invite Professor Ken Grattan to say a word or two to all the members today. We have Dato' Muhammad Yusuf and Professor Noor Saada. If you want to say some good things, okay, the mic to you.
Good morning, everyone, and thanks to Professor Harith for his very warm welcome and for his kind remarks. It's a real pleasure to be here this morning, to be asked to give a presentation and to talk a little bit about our cooperation. So perhaps if I could just share my slides here. Let's just see if I can find the right share.
There's a button, a 3-dot button, sharing your slides.
I've got just looking at the present. So let's see options. Let's have a look. I've used this before, so present your entire screen. Let's see what I can come up with. No, that's not right. So I'm just finding my share button here.
There is one square box with an arrow there.
Yeah, that's the one I'm looking at. Yeah. So present a window.
Okay. Present a window. If you have in terms of tab, you can have. If you have in the term of tab, then you say you can share in terms of tab, a tab. Or if you have open a window, you can share with a window.
Okay, let's just open. All right.
Complicated all these things, Professor Ken.
Is that working?
No, we're still not seeing anything yet. Okay, now should be okay. All right.
Good. I'll just give it full screen. Is that okay? Got it?
Yes.
Great. Okay, thank you. Good. Okay, so again, just to comment a little bit on our partnership before I move into my presentation. I must say that I echo the comments that have been made about the success of the partnership that we have had. And indeed, in spite of the COVID situation in both countries, I'm delighted to say we can report real progress on this particular piece of work. And I think really one of the keys to the success that we have is this long-established partnership that we have between Malaysia and the UK, between the University of Malaya, the City University of London, and the University of Southampton, all facilitated by MITE and by the Newton Fund. We really have worked together very successfully. We can, I think, make very good applications for grants because we know each other's strengths and we can build on each other's strengths. And in that way, what we can create is an extremely good grant application, and even more important, we can deliver on that. I think if we look really at what are the successes and indeed the benefits of the partnership that we have, then I would suggest really that long-standing and good working relationship between the partners really underpins where we are at the moment. That has been critical, I think, to the success we have had. And I think, secondly, we've been able to make impact through grants like this and through the support of MITE and the British Council over the last decade, really, but particularly in this work that we've been involved in over the last couple of years or so. And I think the key thing is impact. This is not just work that is going to be done in the laboratory, gives everyone a nice sense that we've done some interesting science and then just forgotten it. But what we're doing is we're producing work which we're publishing, and then more than that, we're actually taking it into the field and then using it more widely than that. So I think as well, the critically important thing is that we're tackling issues that really matter. And landslide monitoring is an issue that's important to Malaysia, but actually it's an issue that's important to the UK as well. And I think you'll have seen perhaps in the last couple of months some of the problems of flooding in Germany. In the UK, we've had flooding like this as well over the last few years. And the monitoring of banks and of earthworks is critically important to prevent even more damage and loss of life when flooding occurs. I think as well, we've been very fortunate to have the basis for organizing some excellent international events. And this conference is one such event where we can get together and present our work and present our expertise to a broader audience. And in that way, I think to show off the potential that we have for future funding to build on some of the breadth of the work that we've done over the years. And of course, we've been able to create a significant body of publications in the major international literature. This is really a way by which we can share the successes of the work with the community out there. And in that way, what we can really show off is just how good the results have been and how practical the results have been. And as Professor Harith has said, we're publishing in Q1 journals with high impact, and in that way getting our message across to the best audience. But I think it's, as I say, this comes from the synergy of expertise that we have in optical fiber technology, in sensors and instrumentation, in modeling and simulation, and as well in staff and student exchange. Under normal circumstances, we visit each other's laboratories regularly. We sit down and have brainstorming sessions, and in that way, we're able to move forward the progress of the work. Those brainstorming sessions have been done by Zoom and by Google Meets and so on, this time rather than face-to-face. And that's a shame because when we meet face-to-face, I think we get a certain amount of energy from spending time with each other and working with each other. But still, it has worked well under these difficult circumstances. But I would suggest that really what is critically important is that even with the COVID restrictions in both countries, and indeed one of the problems has been sometimes that the restrictions have been out of phase that when work can be done in Malaysia, then there are restrictions in the UK and vice versa. Although we've always tried to use the windows of opportunity that we have to full advantage. So in that way, when laboratories are open, what we aim to do is to make sure that we can work together and that we can take full advantage of the opportunities that we have. And also, I think this has facilitated the writing of papers. Just at the weekend, we were exchanging papers and so on. We a draft of paper written in Malaysia, commented upon in the UK, some additional work done and added to in Malaysia, commented again upon in the UK, building up the papers and creating a paper that has all the right information that we are confident will meet the standards of these high quality Q1 journals and of the referees. So we're continuing to work collaboratively and I think very successfully. And as has been said, we've been publishing together. These are just a few of the papers that we're working on at the moment. Indeed, that we're not just working on, but have been published over the last few years. And as I say, that even at the weekend, where we've been working on additional papers, so that we can build up a strong impact in the literature across the world on the work that we're doing. Again, celebrating and recognizing the fact that the cooperation from MITE and the British Council has been successful in enabling us to move forward with some excellent work. And as I say, my colleagues are going to talk about that as we move forward. So with thanks to our supporters and collaborators and funders, let me just move on to my technical presentation.
Prof, before you go, we have to end the opening ceremony first, then we will
Yes,
start.
sure. Okay.
In fact, I think not to take any more time from our distinguished guest, Dato' Muhammad Yusuf, as well as Deputy Vice Chancellor Professor Noor Saada. On behalf of the organizing committee, we are very grateful, extremely grateful for your presence and for your wonderful speech. And we would like to thank you for finding the time this morning to attend our session. So there is, saying that this online, I cannot show by show of hand to clap, even unless somebody can clap somewhere. I think there's a function to clapping hands somehow. Okay, so okay, you want to say something, Professor Noor Saada?
No, sorry, I pressed the wrong button.
Okay, we want to clap away. So thank you again, and do have a nice day and a good day ahead. And thank you, Dato' Yusuf, and also Professor Noor Saada. And we won't take any more of your time. And I hope next time we're having a workshop somewhere end of the year in Pulau Langkawi. That will be a physical workshop. I mean, face to face and so on. Hopefully by then COVID is over and done. All right. Okay. Okay. Thank you very much.
All the best.
Bye bye, everybody.
Okay. Bye bye now.
Bye.
Okay, now Prof. Ken, I will chair the session. I will introduce you to all the participants. Professor Ken T.V. Galton graduated with a PhD in laser physics from Queen's University of Belfast in 1979 and became a research fellow at the Imperial College of Science and Technology in 1978 to work on advanced photolytic driver for novel laser system. In 1983, he joined City University of London as a new blood lecturer. During that time, they have a scheme called New Blood Lecturer. I can still remember when I was a student in Swansea, there is a time when they have this program by Margaret Thatcher, New Blood program for taking new staff for department to complement the existing senior staff. Being appointed Professor of Measurement and Instrumentation and Head of Department of Electrical, Electronic and Information Engineering in 1991. He obtained a DSc, Doctor of Science, from City University, London in 1992 for his work in sensor system, and was President of the Institute of Measurement and Control during the year 2000. He was awarded the Calendar Medal and the Hanover Prize of the Institute of Measurement and Control. He is now Director of the Institute of Sensor and Instrumentation. He was elected a Fellow of the Royal Academy of Engineering 2008 and holds a Royal Academy of Engineering Research Chair in Scientific Instrumentation. He is also the author of over 700 publications in major international journals and a similar number of key conferences worldwide, and is a co-editor of a 5-volume topical series on optical fiber sensor. And he is the right person to have the opening talk for this morning. A world-renowned figure in optical sensor, and his talk for this morning, if I have the opportunity to introduce, Professor Ken Grattan will give us an introduction talk, Introduction to Optical Fiber Sensor and their use in industry today. Please, sir, you can take over the mic and give your presentation. Thank you very much for being around at 3 o'clock in the morning. We feel so guilty. Okay.
Just see if I can share again. I think I'm trying to remember how I did this before. I think it was this way.
It's a square box. Square box.
Yeah, that's right. It's just. Is that okay?
Yes, it's coming well, sir.
Great. Okay, great. Thank you very much, Professor Ace, for the warm introduction and the invitation. What I'd like to do today is just talk a little bit about some of the background to optical fiber sensors and a few examples of work that we've done at City, really emphasizing the value of optical fiber sensors for environmental monitoring. My colleagues will talk about some of the more specific work and more specific illustrations in relation to the landslide project. And what I'd like to do is just to expand upon that and really think about the fact that optical fiber sensors can be used quite widely for environmental monitoring in the broadest sense of the word. And that's particularly important. So, as I say, what we aim to do in this field is really exploit some of the development in communications and look at ways in which we can create a more green environment through optical fiber sensors. And I'm going to try and very quickly give you just a flavor of some of the things that we've been doing through a number of illustrations here, which really all impact in different ways on our environment. But before that, just to say in one slide, really just what photonic sensors, optical fiber sensors are. And really they reflect the parallel between electronics and photonics. And optical fiber sensors are photonics based, and in that way take advantage of photonics in the way in which recently work has taken advantage of electronics to do better sensing. I think really the advantages of photonics are that they can combine many measurements. They are small and lightweight, and of course being electrically insulating and safe with no currents flowing at the sensor head, then it means that they can be used in environments where it's difficult to make measurements otherwise. And a good example is this bridge strain sensor system that You can see here we built this system some years ago, and the graph shown here reflects one of the measurements of strain on this particular bridge. And sensor systems like that can be used really to monitor what's happening on the bridge and to give assurance that it is safe in the long term. So really, what are the drivers that have taken us from optical communications to optical sensing? And I would suggest that they are in relation to work on distributed optical fiber sensors, and Professor Brambilla will talk about some of those in his presentation a little bit later. We have many different types of fiber available, not just communications fiber, and this gives us more scope as well. We have seen over the last number of years a number of compact, low-cost lasers and other different types of photonic devices all available on the market that we can use in optical fiber sensors. And microstructured optical fiber has been developed and tested. And again, particularly the University of Southampton in the UK has been a pioneer in work in this field. And this gives us much greater scope in the design of the sensors that we can use. The growth in the number of and power of LEDs, light emitting diodes, and particularly at short wavelengths, from the green through into the blue, through into the ultraviolet, again, opens up many possibilities. And of course, one of the most significant factors has been the exploitation of optical fiber Bragg and long period gratings in our sensor systems. And all of this really has enabled us to look at instrumentation, new types of instrumentation for challenging applications. And so in that way, what we've been able to do really is to take some of the best features of the optical communications market and then exploit it in the sensors field. Optical fiber sensors are a growth area, and this slide gives an illustration of some of the potential growth. I think it's probably a conservative estimate to say that in a year or two that the size of the optical fiber sensor market will be about $3 billion US. I suspect it may increase beyond that as well. And as I say, there are two key things here. We have technological growth, technological advances such as I have discussed, and then we have applications which have been driving it. So if you take the fact that we have the technology and we have the applications in areas, military, of course, security, automation, transportation, the biomedical field, and oil and gas, all of those are still very important areas which are driving this growth. And I think from that point of view, if there are young researchers, students, or young postdocs listening in to this particular presentation, then what I would suggest is that it's a very good area in which to work and to build your career. So a number of different sensors are based on optical fiber Bragg gratings. And the big strength of the optical fiber Bragg grating, as this illustration shows, is that what you can do is encode information in wavelength terms and not intensity terms. So therefore, in the bottom, you can see that you cut out a part of the spectrum that goes through the grating at a longer wavelength in the red than in the orange in the top. And although this is just an illustration, it shows you the principle by which the fiber Bragg grating works. And we've used this extensively in the sensor systems that we have developed. A further strength of optical fiber sensors is the ability to create multiple channels. And there are various ways in which you can use multiple wavelengths across multiple channels. The real strength of optical fibers for sensing is that you can put a number of different wavelengths on a single channel, and you can separate them out very easily. That under most circumstances, you don't get particular crosstalk between these different channels. And so in that way, you can multiply the number of sensors that you have simply by increasing the number of channels. And the combination of wavelength division multiplexing together indeed with time division multiplexing across the number of channels gives you enormous scope for large numbers of sensors in any application. So coming back to the slide that I had, I want to look at several different areas and just give you a flavor of some of the things that we've been doing. Really the theme of my talk is that what we're looking at is optical fiber sensors are supporting creating a cleaner environment. And the underpinning theme really is that optical fiber sensors can support reducing energy use, the reduction of emissions, and really help to monitor our environment better. And we can do that through both physical and chemical sensors. And there are different ways in which we can achieve that in different sensor systems. And some of the pictures here are just illustrations of how we can do that. So I'll be more specific. I'll rush through these pretty quickly. But if anyone wants to get more details, please contact me by email and I can provide those details. First of all, in the UK, we're really moving forward with a transport strategy that involves rail electrification. I think the UK is somewhat behind other parts of the world, and in particular, the enormous progress that's been made in Asia, in Japan and China on the development of electrified railway systems is very, very impressive. We have been slow to follow that. But we're catching up, at least trying to move forward within the constraints of the UK and where the railway lines need to run. To do that, what we've been creating is an active pantograph, and this is a piece of work that's we've been involved with for some years, where the pantograph moves across the overhead wire to pick up the energy, the power that drives the train. And one of the challenges has been to monitor the relationship between the pantograph and the contact with the wire, and to do that in a safe way, because you're operating at high voltage, you're operating under vibration, you're operating under different weather conditions and so on, different temperatures. So it's quite a challenging application. So what we've done is we've created a system using an array of fiber bright gratings, working with the UK's major manufacturer of pantographs, and in that way creating sensor systems that can be mounted on the pantograph and then connected back to an interrogation system on the train. And we have active temperature compensation built into this. This gives an illustration just of some of the testing that we've done against vibration. You'll be aware, of course, that in a train, particularly at high speed, you get considerable levels of vibration. And what we've done, again, is created a vibration sensor that goes with the force sensor that we've been measuring to enable us to monitor the vibration in the system. This illustration here shows you just the what we've been doing, and the red line shows the prediction of the pantograph position with respect to the overhead line, and in the top left-hand corner, the contact force, again measured in real time. And what we've been able to do is to, through a series of tests of the systems that we have developed, working with partners shown below, to monitor both the contact force and to monitor the position with respect to the pantograph. And we're currently working with Bracknell Willis and with Network Rail. We have spun out a small company to take this work forward. and in that way to see impact being made on the environment through the fact that we can create a more reliable service using this instrumented pantograph. So we can measure position and force. So this is something for the railway industry. It requires, I think, an interdisciplinary approach which brings together the hardware and the software, and in that way provides data which enables better management of the pantographs. And some data from a run that we did fairly recently. You can see here that what we've been able to do is monitor contact force, speed, vertical acceleration, and longitudinal acceleration. And then the top is shows you just how that varies across a significant run, measuring both acceleration and at the bottom speed here. And you can see contact force and speed on a narrower run across a 10-kilometer or so distance, monitored with our system. What's interesting is that if you look at a snapshot of the data, then you can see that at the middle of this particular graph here, the contact force rises to about 250 newtons. And you can see that the normal contact force is somewhere in the region of about 100 newtons. And so when it gets to these very high forces, then there's the potential for danger and for damage. And so what we're careful to do is to be able to monitor these high forces, and in that way to provide preventive maintenance for some of the issues that there are around the use of this particular system on lines which may be damaged by the contact force of the pantograph on the overhead line. Second area that we've been looking at is in relation to more electric aircraft. I think what we're seeing is the development of electric aircraft moving very quickly. This is just a little clip from the Times newspaper in London a couple of months ago, just showing that the aim is very much for the flight of the future to be electric, and with that, the need for monitoring of the electrical systems on aircraft. And indeed, this is again another picture from the press release from last year. Really aiming to show that with these smaller aircraft, the under 100-seater aircraft, the drive to produce electric aircraft is moving forward very quickly. Predictions about aircraft being in service in 2028, I think, are perhaps optimistic, but I think it's just a question of when rather than if. And so as far as monitoring electrical systems are concerned, then optical fiber sensors are well suited to that. They're lightweight, as I said, they don't have currents flowing, and therefore there's no risk of short circuiting. And we've used optical fiber sensors to measure important parameters like temperature, vibration, torque, speed, and indeed spinning distance. All of these to replace conventional sensors. And this is just a picture which illustrates the fact that on the left-hand side, we have a 19 thermocouple system, and you can see the number of wires and connections that's involved. And on the left, we have a system where we have a motor instrumented with 48 fiber bright grating sensors to measure multiple parameters. And it's neater, it's lightweight, and it's much simpler to implement. So, as I say, we're monitoring these this range of parameters by putting optical fiber sensors into an electric motor, working with colleagues at the University of Nottingham in the UK. And this gives you an illustration of some of the outputs that we have working here at Nottingham. And on the right-hand side at the top, you can see the raw data, the output from a number of optical fiber sensors that have been installed. We've been able to use those in different ways to monitor different parameters. So we have here, again, some measurements reflecting the spinning of the device, the frequencies that are being monitored. And in that way, really picking up the key parameters of the electric motor here. And what we have here is just an illustration of the dynamic sensor response, where we can, as a result of the measurements that we're making here, pick up on vibrations, on the mechanical and electrical frequencies, spin direction, and rotor position. And all of this using optical fiber sensors installed within the motor. A further area that's important really for our environment is structural health monitoring. And we've used these sensors to monitor bridges, foundations, tunnels, and indeed wet concrete. And these are just illustrations of some of the sensors that we have developed and used over a range of projects. And really all of this forms part of an important area of smart asset management systems. Our infrastructure is multi-billion dollar infrastructure across the world, and in individual buildings and structures and so on are typically worth millions of dollars. So we need to monitor those to get the best out of them. And in working with our colleagues at University College London and a commercial company called Macrete, which produces precast concrete devices, then what we're able to do is to monitor the curing of concrete. And one of the biggest environmental polluters across the world is the energy that's involved in the production of concrete. For each ton, 150 kilograms of CO2 is emitted, and there are vast numbers of projects across the world which are using concrete. And part of the problem is that steam curing, which is the means by which concrete is hardened, is inefficient and highly energy consuming. So what we've been doing is using sensors to create microwave curing, and with our colleagues at UCL and an industrial company, Industrial Microwave Systems, we've been able to produce an industrial scale oven, which enables us to monitor, to cure concrete, and then through our optical fiber systems, which monitor temperature and humidity, to be able to monitor what's actually happening, and in that way to reduce energy consumption. And this is just an illustration of how in the automated concrete curing cycle that's shown here, that we're able to reduce energy. The aim really is to create the concrete temperature, which is shown here in the graph on the left-hand side in blue, at about 80 degrees Celsius. In that way, the concrete is not heated beyond 100 degrees, and therefore the steam, the water in the concrete would then boil, create steam, and rather like putting an egg in a microwave oven, explode. No, it keeps it at a temperature where the water remains liquid. And in doing so, what we have is the microwave power that's used, and you can see in the red line here that the microwave power is on, off, and so on. But considerably less power is used in terms of the microwave heating than is seen with conventional steam curing. And the graph on the right-hand side at the top shows that the compressive strength is still the same, even with microwave curing. So what you have here is a situation where you improve the environment, you use 70% less energy when compared with oven-cured concrete. Further piece of work that we're doing with a UK company called Teenbridge is to monitor hydrodynamic performance of marine propellers. and we're looking at a number of key parameters of propellers, which we're monitoring through the use of fiber bright gratings: thrust, torque, advance ratio, and hydrodynamic efficiency, and then comparing these with models that have been produced. And this is an illustration of the vehicle that we've been working with. It's owned by Teenbridge here. It's one of their research vehicles, and we've been able to put optical fiber sensors onto the shafts and onto blades. And you can see here that we have an illustration of the hydrodynamic performance that is shown up in this work. We presented a preliminary conference paper on this at the moment. But what we're able to do is get efficient monitoring of the system in ways that are very difficult with conventional sensors, because there is no commercially available solution for medium-sized vessels, such as the one that you saw illustrated. And we're currently funding this on a proof of concept, which we hope to enable us to take some of these ideas further forward. Further work with another company, Wärtsilä, has enabled us to do larger marine propeller monitoring. And this illustration here on the left-hand side is of a propeller, a 2-meter-sized propeller. And just to give you an illustration, this is a propeller which has a retail value of somewhere between $50,000 and $100,000. So these are expensive items for any vehicle, any yacht. And we have been monitoring with a number of fiber bright grating systems, indeed 320 fiber bright gratings, and then comparing the results that we have obtained with the results of finite element modeling. So on the right-hand side, what we have is an illustration of the strain modes of this propeller through our fiber optic sensors. And so we can produce a number of different sets of data, both in air and most importantly in water, in ways that are essentially important and impossible to do with conventional optical fiber sensors. So in that way, what we're able to do is get some excellent results and compare these with finite element data. And this is just an illustration of some of the graphical data. I think what shows up rather well are the colored illustrations that I mentioned, which enable us to see a close comparison between the monitoring using the optical fiber sensors and the monitoring using the finite element approach. So our ongoing progress to date really has been to demonstrate the potential. We've been working on another proposal with a major defense contractor, and in that way really aiming to show the enormous potential of this in practical monitoring systems. We've created some sensor patches, as we've called them here, and these are being installed, and we'll be doing some tests in the autumn using these systems. Another piece of work, and an important piece of work that we've been involved with, has been with the Sydney Water Company in Australia to monitor sewers, and we're doing ongoing work with them to deal with monitoring using optical fiber sensor systems. In particular, the problem here is that the combination of moisture and hydrogen sulfide creates an acid environment which attacks the concrete, and it creates a highly corrosive environment. And we've been involved really with Sydney Water to try to monitor in sewers. So the big problem is really the fact that we have an acid environment. The solution is fiber optic sensors for distributed humidity and temperature monitoring. And we've looked at a few projects so far on sewers, biodigesters, and we're currently working on structural monitoring in pump stations using our optical fiber sensors. And just to illustrate the sensors that we've been using, you see here on the right-hand side the black commercial electronic humidity probe. It looks nice, clean and shiny. And this is a commercial sensor. And below it, we have a first model of our humidity probe that we produced using fiber bright gratings. And then on the left-hand side, a further refinement of that probe using a fluorinated PEEK polymer. So the key thing has been a sensor packaging designed to withstand this environment. You can see here that really the business end of the sensors, where the fiber bright gratings are shown by the red circles. This is the system set up in Sydney, and these are some results here on measurement of the results, showing that we're able to measure the very high humidity in the 95 to 100% region, but still at the start and the end of this 2-week experiment show that the sensors have a high dynamic range. You can see here just the illustration of the calibration of the sensor, and that black commercial RH sensor that you saw a couple of slides ago, after being exposed even for just 1 month to the sewer environment, you can see here it's looking pretty sorry for itself. It looks very damaged, and indeed it had stopped working, whereas our optical fiber sensor systems continue to work. And you can see here the best of these, the PEEK sensor, in use. And quickly here, really, this diagram shows the sensors after about 3 to 6 months of exposure. Again, surface damaged, but underneath the surface, they still work very well. We've been looking at anaerobic biodigesters, again, where you have the problem of methane as well, causing problems. And again, conventional sensors cannot be used in this situation. We've used 2 sites here and measured what's happening here with the monitoring of the biodigesters. And you can see here the optical fiber sensors being installed, connected in, dropped down into these biodigesters, and in that way enable us to make measurements of this difficult environment. And again, just some pictures here showing the installation site that we've used in Sydney. And as I say, the big challenge here is the presence of corrosive gases, the presence of explosive gases, making optical fiber sensors the best way forward. That's just a schematic of the sensor that we have produced for that specific application. What we have as well is just showing you the interrogation system and the use of lithium batteries so that we can use it outside the laboratory, and the 4G connection for the data collection. And this shows something like 20-month period of collecting of data on humidity, on temperature. You can see on the right-hand side the correlation with the seasons as they change in Sydney, showing that what you have here are the low points in July, of course, due to the fact that that's the Australian winter, and the Australian summer then coming in December, January, showing you the temperature data there. And we had good correlation with our humidity measurement at both sites with that. And again, just an illustration of the way in which we gradually developed and refined the sensors through the course of this particular project. So what we have is a sensor device that does work well in this methane-rich environment. I'm running out of time, and just to illustrate again some of the things that we have done, just to show you that optical fiber chemical sensors, and I really don't have the time to talk about these in any detail, have enabled us to measure things like pH and chloride, which are important for concrete monitoring, heavy metals and pH for soil measurement, drugs and explosives, which link to security, and humidity and moisture, together with pH, which is important again in structures such as you've seen. One particular illustration of this is work that we've done with colleagues in Jinan on monitoring of humidity in granaries, where we need multi-point sensors, and rather similar type of device to the one that you saw for the sewer monitoring. We're using multiple measurements here. And I'll move very quickly through this for time, but you can see here in photograph A, the sensor being installed, B, the electronic sensor which was used for comparison, and then in C you have the connection. So what we've been able to do is get some excellent results here, showing that the optical fiber sensors are capable of giving good results on the measurement of humidity, and do that across a range of sensors with high accuracy. And we did some comparisons here. The black line is the fiber optic sensor, and the red dots are the electronic sensor that's used. And one of the dangers, of course, of the use of electronic sensors here is that it is an explosive environment. The dust in granaries is very finely divided, and it is potentially explosive. And so it's a case where fiber optic sensors offer a safe solution. So let me just finish and acknowledge our collaborators again, and in particular MITE and the Newton Fund. But I hope that I've been able to illustrate the major opportunities that there are for better environmental monitoring, that fiber optic sensors can move from the laboratory into the real world and do so very effectively. You can fabricate them, you can install them, and they show advantages, particularly for highly specialist and sensitive environments over the use of conventional sensors. So with thanks to our funders, particularly for MITE and the Newton Fund, and other collaborators on work on this, and in particular the team at City University of London, who have done the work and gone out to various sites and done the installation and taken the measurements. And my thanks to them for their hard work in doing that. I would just conclude by hoping that it's given you this sense of these real world applications, and that in this way that optical fiber sensors are not laboratory devices, they're real world devices, and there's a lot more to come. There are a lot more applications that can come in the future. So thank you for listening, and happy to respond to any questions either now or by email. Just feel free to get in touch. So thank you very much.
Thank you very much, Professor Ken Grattan. We can open the session for 2 questions. Anybody would like to ask any question, please raise your hand. Anybody want to ask any question? Please proceed. This is the problem with Malaysian audience. They never ask questions, Professor Ken.
As I say, I'm happy to answer any questions that by email. So if anyone wants to email, feel free to do so. I can pick those up and respond. It's not a problem.
But the one that you showed just now, I'm seeing that nobody asked me. I just want to ask you. You indicate the fiber optic for the sewage system. There is a very good opportunity in Malaysia. I think we have our sewage system that they also need to monitor all the gases that come out, especially methane from the sewage system. Can the optical fiber be used to measure methane, those gases, Professor Ken?
Yes, I think one of the important things is that in cities that were created 100 and more years ago, that what you have are very old sewage systems in many places, and indeed many of the records of what are there have been lost. So what you've got is a combination of explosive gases such as methane. You've got problems with acidic gases as well. You've got high humidity, and all of those cause corrosion. And the problem is that nobody really knows where that corrosion is occurring. So you can put your optical fiber sensors into the sewers, and by monitoring the gases and then monitoring the physical changes that the corrosion produces, it gives you an opportunity to better plan the maintenance of sewers, and of course, in that way, really to ensure the reliability of the sewer system that we all depend upon. So I think it has a lot of potential, and a combination of physical and chemical sensors really can give a lot of very useful information.
I think it's a very interesting topic for research. I think for the young people here, you may want to communicate with Professor Ken Grattan on the sensor. It's a very interesting area of fiber optics sensor. If you look at the modern days car, especially Mercedes-Benz, BMW, I think they have tens and of 20s of sensor in their engine system to make the car intelligent. Actually. Okay, thank you so much for your time, Professor Ken. Because it's no, I think there's some function to show clapping. Let me ask my. We should have some function to have a clap somehow. Okay, let me check with you after. Thank you so much, and
thank you. It's been a pleasure.
We are extremely sorry for taking the night away from you.
That's okay. One of the things with international collaboration is that you make things work whatever time it is locally, and that's just fine.
Okay, thank you. Now we go to the next speaker. Let me introduce our next speaker. The next speaker is Professor B.M. Azizur Rahman, a very good friend of our research center, a man that assists us in so many areas and in so many years. We have become very close friends. And Professor B.M. Azizur Rahman completed his PhD in electronic engineering from University College of London in 1982. In 1988, he joined the Electrical, Electronic and Information Engineering Department of City University London, which is now part of University of London now, as a lecturer, where he is now a professor. He is also a member of the Institute of Engineering Technology, and what we have the formula is called IEE, England, Fellow of the Optical Society of America, and a senior member of the Institute of Electrical and Electronic Engineers, United States of America. He has published more than 450 journals and conference papers in the area of optical waveguide, integrated optics, single polarization guide, photonic devices such as high-speed modulator and switches, power splitter, compact band design, polarization splitter, and many, many more. He is also one of the project members in the landslide monitoring project funded by Newton-Ungku Omar Fund. May I welcome Professor Aziz, a very distinguished engineer and also a scientist, I think a very respected person in the world when it comes to waveguide. You can take over, Professor Aziz, to share your presentation.
Okay. Thanks. I will check how to share my screen.
Should I get somebody to help you? I ask Faida.
Okay.
There's one box.
Can you see it? Can you see it?
If you look at the bottom, you see a box here that shows an arrow up, pointing up.
Yeah, I did press that, but let's see again.
You press it, they will have few options. Tab.
Yeah, I did press that. Share, maybe okay. You share.
You share tab or window.
You're presenting your screen.
Okay. Coming now. Okay.
Okay, then I have to.
Aziz, if you open your presentation and then
yeah, this is the presentation now.
Yes, that's fine. So now just make that full screen.
Okay, so it is showing now. Okay.
Yeah, make it full screen.
Okay, is it okay now?
All right. Yeah, it's good now, sir.
Okay, thanks, Dr. Harith. Thanks for the kind introduction. And it's nice to see Ken Gratton in early morning. It's a good morning from London. After an excellent talk from Ken, I'll try to focus more on the modeling side of the photonic sensing. So I'll talk about the photonics modeling methods and some selected results, particularly looking at the innovative or new types of photonic sensor, and then I will conclude. So the photonics is a key technology which is like following the electronic side, and it is a key enabling technology defined by the Horizon 2020 program. Now, the innovation in photonics, initially it started in 1960s with the invention of semiconductor lasers and optical fiber. After that, the major innovations were NBM.5 amplifier and wavelength division multiplexing. There's a lot of work going on now, polarization, mode division, space division multiplexing. But what are the next? We can talk about plasmonics, metamaterial, silicon photonics, and optical sensor is one of them, and I'll talk about this. So in the photonic sensor, the first thing is that, as Ken said, we can use the optical waveguide to both to connect the sensor element or also as a sensor element. Among that, we can use single mode fiber, multi-mode fiber, photonic crystal fiber, tapered fiber, nanowire, slot guides. And also the devices can be arranged in like a fiber bracketing, long periodic grating, integrated optics, Mach Zehnder, plasmonic, resonator, many different arrangements are there. Now, if you look from the modeling side, all these things can be divided in few groups. One of the first thing is that to model optical waveguides. In that case, we say it's a uniform. And for that, what you need is a model solution. However, if the structure is a non-uniform or a guided wave structure, it can be arbitrarily non-uniform when you need beam propagation method. However, if you can simplify this as a butt coupled of few uniform section, the best method will be mode solution plus junction analysis. Besides that, you may need sometimes 3D resonating structure and also another more versatile approach called time domain approaches. So the first thing is the waveguide. Optical waveguide is a key component for optical sensor or even communication. The way we define optical waveguides is that refractive index is function of X and Y only. It is independent of Z. It can be any complex shape and size. The refractive index can be any complex thing. It can be nonlinear. It can be anisotropic. It can be lossy. As long as the refractive index is a function of X and Y only, a model solution is good enough. And for the model solution, you need to define the refractive index as a function of X and Y. And what it can give you, the modal field, and the propagation constant. And for that, from early time in 80s, one of the methods was very useful, popular. It was semi-analytical method called effective index method, developed by Knox and Tolles. It is popular, but then lots of other methods started developing, and so nobody uses it. In the numerical approach, in 90s, there's a one very popular called finite difference method. Most of the commercial code was finite difference, but today, finite difference method is the dominant method today. So for optical waveguide, what you need to consider a wave equation or a type of equation called variational formulation, which its Euler equation will be an wave equation. And I developed during my PhD, 79 to 82, it's an H-field formulation, which is fully vectorial, naturally satisfies the boundary condition, is exact in the limit, and is valid for general anisotropic or all sorts of optical waveguide. And the 5 key paper has been cited 1,500 times. Next, we may encounter 2 waveguides misaligned, and there's a junction there, or a waveguide is butt coupled to a directional coupler. So there is a misalignment, or there's a junction at the middle. Or it can be a single mode waveguide, butt coupled to a multi-mode waveguide. Same way, like you can see, a waveguide can be split into 2 for a max intersection. What you need is a called junction analysis. And for the junction analysis, the fundamental equation is that a tangential electric and magnetic field must be continuous. And that is enforced in the method we developed in 1988. Another method, as I mentioned, is a more versatile, that refractive index is a function of X, Y, Z. Like a tapered structure, which is essentially Z variant structure. So in 1979, Fate and Flake developed a Fourier-based method, which was scalar, and then different research groups started working on finite difference and finite element-based. And we developed in 2000 a finite element-based fully vectorial formulation, and boundary condition is also very, very important for a beam propagation method. Another structure is a 3D, but is a resonating structure, which is like a when you want to study like a whispering gallery mode in a micro resonator or micro resonator or ring resonator. So this is a frequency domain problem. And so what you need is eigenfield analysis. And we developed a finite-based approach recently. The last approach you need for this structure is a time domain approach. Good news is that it's valid for general electromagnetic problem. You can use for all sort of electromagnetic problem, but it is useful for pulse propagation, strong discontinuity, and photonic crystals, nanostructure like that. So it is versatile, is useful, but it is extremely computationally expensive. If you think of that, finite element mode solver, refractive index is a function of X and Y, is a 2-dimensional problem. BPM is a 3-dimensional problem because it is a function of X, Y, Z. And FTDD is a 4-dimensional problem because here X, Y, Z, and T, you are not considering time harmonic anymore. So it is extremely computationally expensive. So you need to use when you have to use it. Otherwise, better not to use FDTD. If you can solve your problem with a mode solver or junction analysis or BPM, better to stay with that. We have tried to develop finite element time domain. It can take advantage of FEM. We did some work, but now we have stopped the work because of the funding we need. So we did work some work in 2013 and 15. So today's focus at City University of London, more than 40 years of research we are doing for fully vectorial and computation efficient finite element method. We have one of the best in-house computer code for photonics modeling. Now we are working on a range of devices, photonic devices, but my focus will be a limited number of results on more innovative photonic sensors. So one of the oldest sort of form of sensor is a surface plasmon resonance. Earlier, people used auto arrangement, but better than that is a Crestman. But these are both used as a bulk optics. Our intention and our focus is more on guided wave plasmonic photonics rather than a bulk optics. This is a fiber-based sensor. It was very popular in the 80s. You have a single mode fiber, you polish the cladding a bit, put a metal coating, and which can excite surface plasmonic wave. But today's focus is more on other, I'll talk about that. So single interface for a metal and dielectric is very easy to solve. You need to solve a transcendental equation, which is rather relatively easy, and you can get effective index from some sort of semi-analytical equation. However, when it is a coupled surface plasmon mode, like you have a one interface, there is dielectric, metal, and dielectric, or in other way, metal, dielectric, and metal. What you get a coupled surface plasmon mode. The top line is a fundamental one, but is an odd-like shape, and the lower one is a even-like shape, but is a second mode. The second mode has a lower loss, and that's why it is also known as a long-range surface plasmon mode. And often, this second mode is used for optical sensor. So although solution for a one-dimensional plasmonic mode is easy, but whenever it gets two-dimensional, it is extremely difficult, particularly when width is comparable to the thickness. In that case, what you can have a mode on the upper interface, plasmonic mode, you can have a mode at the lower interface. And together they can form a coupled mode, which can be even or odd-like. You can also have a mode at the left side of the metal interface, also on the right face. So what you have a combination of these modes, and which is rather complicated. We published in JLT 2017 on that solution. Now for sensing, one of the important things people use is evanescent field. That means how much field is outside the clad. For most of the fiber, if the clad is thick, there's hardly any field outside. If you start removing the clad, you can slowly access the field, but still you can see that whenever you're reducing the clad, it's still only a fraction of a percent field in the cladding region. So better approach instead of that will be to use a microfiber. Here you can see that as the fiber radius, you're reducing from 4 micron to 1 micron or half a micron. You can see the blue line here on the right is the power confinement in the clad is increasing rapidly. And what you can see here on the contour, that in the right one, although the radius core is 0.5, but field is much more mostly outside the core. So this has a more potential as a sensor. Ken Grader has talked quite a bit on the fiber bracketing, which is also used for optical sensing. And another sensing can be useful for planar guide is called Mach-Zehnder arrangement. Mach-Zehnder can be used also in like a tapered fiber where the mode can guide in the core and cladding and multiple mode when you reduce the one. And for that, in a Mach-Zehnder, you have to have a power splitter, you have a sensing arm, you have a discontinuity at the input junction, at the output combiner, and also at the sensing arms. Okay, I think I've shown that. A nanofiber looks very simple. It looks like almost similar as a optical fiber, but an optical fiber, the index contrast is very small, but in a nanofiber, because of the strong index contrast, its solution is not easy. The first thing people quite often make a mistake, they assume that since the structure is circularly symmetric, the solution should also be circularly symmetric, but that's not right. You can clearly see, we published in 2010, that the dashed line is the interface, and you can clearly see the field is not circularly symmetric. Now, why it is not? The reason is The dominant field in optical fiber, depending upon T or TM mode, is the HX or HY field. The boundary condition of HX and HY at the top interface, where the interface is horizontal, or at the side interface, where this interface is vertical, is different. And because the boundary condition is different, that's why the circular symmetry is destroyed in the solution. So that was a simple structure, although the solution was not easy because of the strong index contrast. Whereas photocrystal fiber, widely used in optical sensing, the structure is much more complex. The holes, there can be many rings, the hole can be of different size and shape, and it can be very leaky mode. Again, finite element method is one of the best approaches for the solution. Now, if I introduce even inside there is a defect, and if we now coat with a metal, the physics is now much more complex. And what you can see here, because of the hole, the field quickly starts dropping because there is a low index area. And now if we introduce a metal cladding, then what you have is a plasmonic mode at that metal cladding inside the hole. A gold nanowire is a simple circular metal rod, but again, the solution is not simple. And again, we have shown its solution for different sensing application. So zinc oxide clad gold nanowire, there is a plasmonic resonance, and for that, you have a higher loss in that region. Another sensor you can think is that you have a fiber, you have a cladding, and what you can have a metal clad there. Now, what you can have now, you can have a plasmonic mode at the inner interface, inner surface of the metal and the core, and you can have a plasmonic mode at the outer interface of the metal and the outer one. Now, for a good sensor, the trick is to make these two modes phase matching. And if you can do that, in that case, the mode in the core and the mode outside, they interact with each other. And that is the way you can design a really next generation optical sensors. So the field profile, as I mentioned, in a circular one, that because of the boundary condition, the modes are not circular symmetry. You can see that here, this is the 1/4 of a metal clad fiber. This is the metal interface, and you can clearly see the field is localized in the X side and the Y side, not on the top or at the bottom. Circular symmetry is not there. That is because the boundary condition on the metal cladding at the top and the sides are different. And what you can see here, if I plot the field properly, you can see the field is even like sort of mode, and which is a long-range surface plasmonic mode and can be used for optical sensing. Now, the design of sensor, you can see, one case is the mode in the core, which is mostly is a straight line, but mode at the metal interface was reducing with the cladding thickness is like that. But what happens, they never cross. They call anti-crossing. At that anti-crossing point, their phase constants are, phase velocities are similar, called phase matched, and that's the time it builds up, called a even like supermodes. And that's the position is used for sensing application. And it is showing that in a case like suppose you have a fiber, you have a core, you have a channel, and you did different sort of forms of nanowire and how to model it and sensing it. What important thing is there here, as I mentioned, is the phase matching. Here, this red dot line on the left, it is the plasmonic mode of the metal layer here. And the black line is the dielectric mode. You can see sometimes this is crossing, but in reality it's called anti-crossing here. So at the anti-crossing point, the phase velocity beta for both core mode and cladding mode are similar, and then they mix up. And as you know, the core mode is generally less lossy because dielectric. Plasmonic mode is highly lossy. Whenever they interact, suddenly the loss of this core mode peaks. And that's the peak point we need to use for optical sensing. And this is showing a simple slides and how we get a mode profile. But what we're focusing also quite a bit on integrated optical waveguides. And the reason is that for integrated optical waveguide is the next generation of sensors. The highly integration is possible. It's a low fabrication cost if you do many of them, many produce, and it needs low fluid volume consumption. But challenge is still novel technology. Scaling down of the direction principle you need biosensor compatible material, but also from the design side, it is much more challenging than the fiber-based sensor. This is showing, the left one is a simple silicon nanowire. It is showing the mode field mostly in the core and a bit on the side, but because nanowire, you do see some field on the surface. However, there's a novel structure, is called slot waveguide. There's a two high index material, there's a low index in between, and that field is confined mostly in this low index. And this is a very excellent candidate for optical sensor, particularly planar structure. Instead of having them side by side, if I make two high index vertically separated as a low index area, it can be low index compared to suppose high index is silicon, low index can be silicon, it can be water, it can be air, but most of the field will be in the sensing region. And I'll show you some results on that. Now, how you can do sort of level-free sensing. It can be a slot waveguide, it can be a nanowire, it can be a polished fiber. It can be, you can add a plasmonic layer, but the important thing is that we can look at it can be any one of them, but if you think just a waveguide, which is here, and what you need is to functionalize the surface. What you have, there are lots of things in the adjacent. It can be sensing from the water, urine, blood, serum, but in that there are many, many particles are there. What you need to do is to somehow, if suppose all of them touch the guide, the propagation properties will change without the bioreceptor, and you wouldn't know which one is causing this change. So if you coat the waveguide, whether it's a slot, nanowire, or fiber, with a receptor which has a specific functionality, and suppose that this only attracts this diamond shape, so only when diamond shape is present, then the waveguiding properties will change. So for any sensor, it has to be selective. And now you can look at the integrated optics format or other format. One of the nice format people use is called ring resonator. You have a mode or a resonating point or a ring resonator, and now if suppose that area we functionalize the ring resonator, if anything adds to that selectively, immediately the resonating wavelength will shift, and by looking at the shift of the wavelength, you can detect, and it can be very, very high quality sensor. Now, you can be even more innovative. The ring resonator, instead of using a simple silicon nanowire, you can fill up with a ring resonator with a slot waveguide. In that case, what will happen, because in the slot in the middle is a void, it will be much more sensitive to any sort of analytes in that area. So we look at the early work. It's a simple vertical slot. We look at the silicon covered with a DNA and linker, and we analyze that we published in 2012, and we looked at the design, and typically silicon width, you need around 200 to 250 nanometer to have the best response. We also work on the vertical sensor, vertical slot, where you have a slot. We also fabricated partially in Thailand. And then again, we optimize this numerically, and you can see that how dsDNA and ssDNA, the difference you get, and how we can optimize the sensor design. Cross slot is another interesting, because what is important that vertical slot is only confines the light T mode. Horizontal slot only confines the TM mode. But we looked at the design which is called cross slot, which was the first times we reported things like that. Here it looks like a suspended. Yes, it can be suspended like a cantilever arrangement, and it can be suspended like you can have a horizontal slot in the middle and vertical slot here. And it can be very, very sort of rotation independent sensor. And also here you can see that for this slot, cross slot, T mode confined in the vertical part and T mode confined in the horizontal part. And we can design this structure so that we can have not only high confinement in the slot area, but also have equal confinement. These lines identifies equal confinement, like the red line identifies 35% confinement for both T and TM. Then the slot can be even more complex. You can have a plasmonic slot. You can have a metal one at the top. There's a porous zinc oxide, silicon. So this is a plasmonic slot. One of the earliest work was done in University of Toronto. And this one simulation, you can see clearly, you can see the plasmonic peaks inside the slot for the simulation. And now what you can have a different arrangement like a laser, power splitter, sensing out, combining them, and you can have a more sort of innovative sensors. We also work like a different sort of sensor here. In this case, gold is the lower, silicon is the up. This is suspended, and it can be sensed for both different diffractive index of both biomaterial or other analytes that we published in Sensors and Actuator. We also looked at the very sort of innovative sort of thing, because as you know that we have shown that ring resonator is quite interesting and well explored for optical sensor. Ring resonator is a round, is a circular, and because of circular shape, there will be some bending loss. What we have proposed here, instead of a circular resonator, we have a short section of horizontal section. This is slot guide, but as a resonator. And if we can use as a resonator this part, like a Fabry-Paro resonator, and then we can have a very, very new type of optical sensor without resonator, but without using circular section. And because of the resonator, now what we developed for this particular work, we developed a three-dimensional finite element code to analyze, to find the resonating mode of that resonator. And that then we have, this is a new code we developed, the three-dimensional finite element, and we use it then to find the sensitivity of different analytes. Now, one thing we talked about is a fiber Bragg grating. Fiber Bragg grating is extremely useful for sensing temperature, humidity, and strain. And because somehow we influence this influence the periodicity or pitch of the fiber Bragg grating. But if I want to use as a biosensing, and if something is attached outside, it normally doesn't work because you don't have much field outside the fiber. The most of the interaction is going inside the fiber core. So quite often what you have to do, you have to etch the fiber grating, and then use all sorts of technique you learn about analytes, about nanowire, about graphene oxide, you can use it. So what is important is that fiber Bragg grating straight is not that good for surface sensing. So that to do that, you have to etch to enhance the evanescent field. But what it does, it also weakens the structure. And so what we consider later on is that instead of fiber Bragg grating, uses long period grating. Long period grating, there is the cladding mode, it comes outside the core. So if you have analyte at the cladding, it will affect the cladding mode. And so without etching, you can use as a sensor using LPG. And you can see the field. This is a suppose 9th mode, LP09, and it is the mode field profile. You can see the field profile. it is tiny at the edges. It is true. But by using the analyte, you can see on the top diagram that the confinement in the analyte will increase 29 times because of this. Whereas if you use fiber bracketing, because of the fundamental mode, there will be hardly any field at that cladding. And this thing we set up for the laboratory work in Ken's lab. And then these are coated with a multi-layer coated. And then we check them as a cross-sectional area of the fiber. We also did that SEM image and also looked at that, confirming that what other things are there. There are lead and other elements are there. So this is the setup for this experiment. And if I look at the simple schematic, there's a light source, there is a long period grating here, and it was detecting the heavy metal in water. And for that, there are different long periodic, there's a mode, and in this case, higher order mode is much more sensitive, and we use that higher order mode for the bear and this with the sensing. You can see that there is a shift of the peak. So this shift of the peak identifies the component here. In this case, is a lead. In this case, a mercury here. So you can see that is even 1 micromole is detecting as a shift of the this spectrum, and which you are looking at the spectrum, and that identifies the contaminants. Here you can see that it is very sensitive, below, even in a nanomolar level, 10 nanometer, and they get saturated. So obviously, to identify this part, we can design a sensor which is less sensitive, and this part can be more sensitive. And if I expand it, we can see linearity in this part. But also an important thing is showing that this sensor has been designed so that it's sensitive for the lead, but not for mercury and chromium. Then you have to design other sensor which is sensitive to mercury but not lead. So this is showing clearly that cross sensitivity is much smaller. And this is showing the linear part of the wavelength attenuation there. And another thing that we did work is called dual peak long period grating. You have 2 peaks, and that you can design by dispersion engineering of this sort of fiber. And what you can see, this is a simulation, and that is the experimental measured data for the peak one. Then this dual resonance is a nice, interesting thing where the resonance peaks, one of them shifts left, one of them shifts right, and that's why its sensitivity is double of the normal long period grating. And what I did also later on, we use the long period grating, but as it is also changes the sort of wavelength shift with the temperature. So there is also a fiber bracketing is a butt coupled to that, and 2 together it produces a temperature independent sensor. Then also we use that machine learning so that we can improve the solutions, and this shows that the limit line of directing limit can be as low as 0.2 nanomoles. And this also shows the selectivity. This particular one was designed for the lead sensor. It does respond to the other, but a smaller amount, but is designed to be more sensitive with the lead. And this is showing that as the lead concentration is increasing, the value is increasing, and as you clean it, it is reducing, and so it is showing the repeatability of the sensor. Ken probably has talked about this, so I will detect, this is natural organic material. What we have done, that there's a multi-core fiber, and we looked at the fluorescence base for this natural organic material sensor.
You have about 5 more minutes, no?
Okay, so we are nearly finishing. So we are doing this one. This is a work with Sydney water, and using them in a multi-core fiber. So it is looking at the fluorescence material for different sort of contamination. So the collaboration, let's acknowledge it. We got fund from the Newton Fund, also NARC, Royal Academy of Engineering, Researcher Link, British Council, and MITE is also part of this Newton Fund program. So in conclusion, we can say that we have been working for more than 40 years on the development of rigorous full vectorial, computationally efficient, finite element-based numerical methods. Today, briefly, I presented some results focusing our work on modeling aspect of optical sensor. Thanks to Dr. Harith for organizing this conference, and thanks to MITE and also Newton Fund.
Okay, thank you very much. It's a very excellent, interesting talk by Professor Azizur Rahman. May we open the floor to question, one or two questions, but I don't know, our audience doesn't have question. You may want to ask a question. I think it's very important to ask question. We have a very distinguished speaker actually. Now we open for at least for two questions. Is there any question? You can raise your hand. Any question? They have no question, Prof.
Okay, thanks. If the one that can, if they write to you or myself, then we'll be happy to discuss anything with the PhD students or postdoc. Thanks. Thanks for organizing it.
Okay, thank you so much.
Looking forward to see you soon.
Okay, we show our thanks to, there's no symbol to clap the hand. We show our thanks to Professor Azizur Rahman for finding the time, because he is in the very early in the morning, I think 3 or 4 o'clock or 4 o'clock in the morning. He takes great effort to stay awake or wake up very early to give a talk. So we are so grateful to you, Prof. Thank you so much. We are extremely
grateful. Thanks.
We go to the next speaker. Our next speaker is Professor Gilberto Brambilla. He'll be talking on distributed optical fiber sensor and landslide monitoring. I will just introduce him to everybody. He's a good friend of Photonics Research Centre. We have frequent exchange visit with Professor Gilberto Brambilla. He's from Optoelectronics Research Centre, University of Southampton, UK. ORC is one of the most advanced and one of the premier centers when it comes to photonics in the world, actually. All right, then you have other from Denmark, maybe from US, Arizona. Professor Gilberto Brambilla is a professor in photonics at the Optoelectronics Research Centre, University of Southampton, UK, and the General Manager and Deputy Director of the Future Photonics Hubs. He obtained his MSc Material Engineering with honors from Politecnico di Milano, Italy. It's another top polytechnic in Italy, in Milan, very nice place. And his PhD degree in optoelectronics from University of Southampton. In 1996, there's Milan, and 2002 from Southampton, respectively. In 2007, he was awarded a research fellowship from the Royal Society, a very distinguished fellowship. He has been the director of the EPSRC Center for Innovative Manufacturing in Photonics until 2015. He has published over 300 papers in international scientific journals and conferences, author of 4 patents, and gave more than 30 invited keynote plenary talks over the 5 continents within his career. He's also one of the project partners in the landslide monitoring project funded by Newton-Ungku Fund. He's a very brilliant chap, very clever chap, especially in photonic application. I don't understand we have this problem, Prof. Gilberto, our audience, they will listen, but they have no question. Sometimes you wonder what do they listen actually. I think it's very important. I think we have been trying to find ways to make our audience ask questions, actually. They are very shy people. I think you can start now, Professor Gilberto. Thanks for coming. Sorry, my apology for early in the morning that you have to stay awake. You can start now, sir.
It's okay. Thank you, Prof. I think they will be able to contact us by email if they are really shy. It's not a problem at all. I would try to share my oops, it doesn't let me share. I hope everyone can see it now.
Yes, Prof. We can see now. We can see the screen sharing now. But we are yet to see the document.
Can you see the document?
No, there is no document appearing somehow.
Oh.
Can you try again?
Gilberto, Ken here. I think if what I find is that if you open the presentation and then shrink it, you can you'll then see it as one of the windows.
I have opened the presentation.
No.
Can you see now?
We see many.
Can you see the presentation?
Can you try again?
Apologies for this.
Yeah, that's good. That looks right.
All right. Okay, that's good.
Apologies for that. Okay, today I'm going to present the work that has been carried out in my group and more generally within the Future Photonics Hub in terms of distributed optical fiber sensing. So far, you have seen from Professor Ken and Professor Aziz examples of point sensors. Me and Professor Zaini will talk more on the distributed sensing part. So I'm sure everyone is familiar with the internet. And the optical fibers constitute the backbone of the internet. So far, more than 1 billion kilometers of fibers have been deployed. And you can find them actually pretty much anywhere. This is a map that shows the undersea connections between the different countries. And you can see that there are fibers under the Atlantic Ocean, under the Indian Ocean, connecting the Pacific Oceans to Australia, Asia, Africa. All the continents are well connected. And the idea then comes, why don't we use some of them for sensing? And this is particularly useful when you want to measure environmental changes that occur on a large scale. But distributed sensing doesn't focus only on large scale. It can be found also in plants. So this is, for example, a way lots of different sensors are connected within a manufacturing plant. And there are point sensors and there are distributed sensors that are placed all across the manufacturing plant. So the focus of the hub is on 4 different technologies that are supposed to support the different fields of photonics. Metamaterials and 2D materials, where we have 3 main investigators, light generation and delivery, optical fibers, and silicon photonics. And all of them then merge in the grand challenge of integration. And my group focuses on this, on the integration of the different technologies, and in particular focuses on the integration into sensing architectures. And the hub has received quite a lot of income from the industry over the last 6 years, and this is what we got for the different platforms. Integration is the smallest of all at the bottom, with only 657,000, while fibers that are a more mature technology got in excess of 5 million. Nonetheless, sensing is really interesting. The problem is that we have a very tough competition because there are lots of different types of sensors. So we have electric or electronic sensors that tend to be very cheap. We have micromechanical sensors that are easy to manufacture. We have integrated photonics that can manufacture in batched, and photoacoustic sensors that exploit the sound capabilities in order to detect chemicals to very small levels. So there are lots of different sensing approaches that are very competitive, especially in terms of price, with respect to the optical fiber sensors. And finally, there are microfluidic sensors where the optical part is then shared with the fluidic part to monitor more complex quantities. So why do we focus on optical fiber sensors? The reason is that they are not affected by electromagnetic interference. Like, for example, in UAVs, they are particularly good. They can work in harsh environments. They work over very long distances. And they cost very little when you consider what is their cost per unit. But above all is what Professor Ken mentioned at the beginning of this seminar, which is the massive parallelization. So either, no matter whether you use gratings or distributed sensors, you can still integrate and parallelize all of them so that you can interrogate loads of different sensors from a single unit. This is an example of how sensing, optical fiber sensing, can be used within a smart city. And most of them tend to be point sensors, with probably the only exception of the structural health monitoring. But if we focus on specific sectors, then you can see that distributed sensing has loads of applications. I chose the oil and gas because is where probably optical fiber distributed sensing has had more success. It's used in seismic monitoring, so basically monitoring earthquakes and the fingerprints that is associated to the different ground density. It's used to monitor land wells, so to monitor how well it's working, what is the flow versus time, whether it's getting clogged up, because operating land wells is very expensive. And therefore, if there is a problem during operation, means losing lots of money. Typically, land wells generate in excess of £1 million per day. So having the well down for a single day is already expensive. If there is a major problem and the land well has to be closed for months, then you see that the financial hit is significant. And then there are refineries and pipelines, which are very, very vast in terms of surface and length, and therefore need some ways of monitoring that is capable to monitor long distances. And then there are offshore wells that are far away from land and therefore need to have some sort of connection, typically underwater, where the sensors are connected to the land. If we have a look at the optical fiber sensors, there are lots of different types. So there are the intrinsic sensors where fiber is used as a sensing mechanism. And then there are the extrinsic sensors. And within the intrinsic, I think the two big families are point and distributed. Point focus on the measurement of a specific target in a single point. Distributed carried out the measurement along the whole distance of the fiber. And if we go down, then we see that there are gyros to measure the rotation within airplanes, the magnetic field sensors and gratings, as you have heard originally from Prof. Ken and Prof. Aziz. Then we have biochemical applications, physical, which are basically strain and temperature, and all of them basically rely on the measurement of a single point. In distributed sensors are usually classified in a different way by the mechanism that is used for detection, and therefore are classified in Raylight, Raman, or Brillouin sensors. And they allow to measure temperature and strain. So these two are the main quantities that are measured by distributed sensing. And indeed, using the measurement of strain, it's then possible to measure vibrations. And this is what we focus in Southampton, the measurement of vibrations. So this is what I will focus on today, the distributed sensing part of the optical fiber sensing family. So distributed fiber sensors are beneficial because if you compare to traditional sensors, these are loads of different sensing units that are connected by lots of cables to an acquisition system, to a data acquisition system. If you look at a sensing unit like this one that has 30 sensors, you realize there are lots of cables that are coming out. Distributed optical fiber sensors use a single detection unit. And so each section of the fiber produces a signal that then is detected by the data acquisition system. And it is detected using time or frequency as means of detection. So it's a technology that enables the continuous real-time measurement of a specific parameter along the whole length of fiber and relies on the backscattering of light within the fiber. There are three mechanisms, as I mentioned, which are raylight, which happens because of the density fluctuations of the material, and is basically backscattering at the same frequency as the light that is propagating into a fiber. Then we have Brillouin, that is the result of acoustic waves within the fiber. And it has a shift that typically is in the region of 11 gigahertz from the pump wavelength. And Brillouin is particularly useful because it can measure simultaneously strain and temperature. Yet it has a drawback with respect to raylight, which is the smaller signal. As you can see the graph on the left, there is a difference of about 20 dB. So 100 times less intensity backscattered. And then there is the Raman, which is basically the inelastic scattering, which comes from the fact that the molecules, the silica molecules within the material, absorb or release some of the energies that intrinsically have. And this provides a shift of 13 terahertz. So as you can see, Raman is, the Raman signal is about 30 dB smaller than the raylight signal. But on the other side is at a different wavelength, which is shifted. So this sensing allows to get rid of the raylight signal with a simple filter. So Raman has its benefit despite having a much smaller signal. If we look at the architectures, there are lots of different architectures, but I think it's fair to say that there are three main architectures. The OTDR, or optical time domain reflectometry, is what we use. And it relies basically on a pulse generator that drives a laser source. The laser emits a pulse that goes into the sensing fiber. Here there is some backscattering. The backscatter signal comes back through a circulator, is amplified, and then goes to a detector after passing through a filter. And in this way, the position along the fiber is determined by the time of flight. The benefit of this approach is that it allows for the monitoring of very, very long distances, typically in excess of 40 kilometers. An alternative approach is to use the optical frequency domain reflectometry. So in this case, the laser frequency is swept, typically between 1530 and 1570, 1565. And the light goes through a coupler to the sensing fiber, and the backscatter light is then combined with a second arm that is not basically the sensing fiber, and is combined at the detector. So this OFDR has benefits of having high spatial resolution, but on the contrary, can be challenging to be used on long distances. And then there is the optical correlation domain analysis, OCTA. So this is a bit more complex and uses two different sources for pump and probing. The drawback of this approach is that it requires access from two ends. So you see that the probe and the pump are coming from opposite directions. So this seems to be a bit more unsuitable for environmental monitoring. So what approach do we use within the OTDR? We use a so-called phase OTDR or phi OTDR. So when we launch a pulse into a fiber, there are reflections at different positions. And these two have different phases. So they will provide an intensity which basically depends on the phase relation between the two backscattered contributions. If there is strain, the two positions move apart, and the backscattered then have a different phase relation. And this means that the intensity that is monitored by the detector then changes. By monitoring these changes with time, it's then possible to determine what sort of vibration is present in that position. Now, in practice, we have a source that is driven by a pulse generator, goes through an optical isolator and then a coupler, and this is amplified. The amplified signal then goes through a filter so that we have a very narrow signal and goes into the sensing arm. So what you see at the bottom here is the lab equivalent of the fiber that we deploy on the field. The backscattered light then goes through a circulator, through a detection system. Basically, we have here a Mach-Zehnder interferometer, where we induce a phase difference between, we induce a delay, basically, and then we have three photodetectors that continuously provide signal to the oscilloscopes and then the phase detector. In practice, our unit looks like this. This is our portable unit that is ruggedized and field deployable. We send this to Japan, we send it to the Philippines, and at the top you see the computing part where there is written Dell. At the bottom is the optical part. So there is the data acquisition system is just in the middle. This can operate over distances of 30 to 45 kilometers. It has a spatial resolution that can be typically between 0.5 and 10 meters, and a frequency range that can go up to 20 kilohertz for short distances and 0.1 hertz. The sampling rate is as high as 300 megasamples per second. So what do we use this for? The sample that we sent to Japan, and is actually there, is based in the south, not far from Osaka. Is actually on this little island that you can see here, where the JAMSTEC, which is the organization that monitor tsunamis and earthquakes, has the donut system. Here you can see the island on the top left of this insert, which is basically this island over here. And from the coast, there is an optical fiber that goes down along the fault between the Philippine plate and the Japanese plate. And there are lots of seismometers connected to that. We connected our unit to this fiber, and we monitor constantly any tremor or any slide, underwater landslide that happens off the coast of Japan. So this is a schematic of how it looks like. We have a building, which in reality looks like this. We have the fiber that goes underwater and goes up to, I seem to remember, 50 kilometers, where there is a unit to monitor the bottom of the ocean. And the place where the water gets into the fiber gets into the water is here. Looks like this. So we have the water that is basically under these rocks and goes for another 50 kilometers to a depth of few thousand meters. These are the traces that we record from the unit. So on the right, you see the distance, and along the vertical direction, there is the time. What you see on the left here, which is magnified on the left graph, are waves. So we are basically monitoring the movement of the waves versus time. And here you can see how the waves are moving along the y-axis, so along the time. So a wave in this point is moving and is hitting the coastline at this point. I need to point out that here is a depth of a kilometer, in excess of a kilometer. So we can monitor waves up to the depth of about few hundred meters. And we can detect them actually even further, at depths in excess of a kilometer. But in this area, what we detect better is the movement of the ground. This is a single wave that is moving along the distance. This is a graph that we took when the weather was quite good. And this is the graph that we took when the weather was quite bad. So you can see here that the waves can be detected up to a depth of a kilometer and a distance of 2 kilometers from the shore. We still can resolve each single wave moving. And on the right, you see that there is lots of different noise coming from the storm that was hitting this part of the Japanese coast last week. The problem is that if we have a look at the distance and the signal that we get, we reach a point at about 50 kilometers where we cannot see anything. So we have amplifiers both in the source that we send that is used to send pulses to the sensing fiber, and in the backscattered signal detection system. So we have two EDFAs simply because the signal is very, very small. The solution to this is to enhance the backscattering. So this solution was proposed by Sasha Lear and his colleagues some 8 years ago. And he used some laser to make some holes into the fiber and increase the scattering. Now, this worked very well. It increased the signal by orders of magnitude, but increased the loss as well. And therefore, the loss that was observed in this fiber was in the region of dB per meter. So while this is a good idea, it doesn't work for long distances. Hydrogenation has been proposed as well as a solution because it increases the scattering by 2 orders of magnitude, as you can see in the sections C of this figure. The problem is that there is also a 20 dB increase in loss, and therefore it can work up to a kilometer, and then it doesn't provide much benefit with respect to the normal fibers. Flogs have been proposed by Luc Thevenard and colleagues, where a continuous long grating is inscribed in a fiber. This can increase significantly the backscattered signal. The problem is that it's very difficult to manufacture, and only meters have been made so far. Fiber break gratings, fibers, so basically gratings that are manufactured in the fibers during manufacturing, have been used in the oil industry, and they provide an enhancement of 10 dB, an enhancement of 30-40 dBs. The problem is that they also provide a loss of 10 dBs per kilometer, and therefore they extend the range of distributed sensing only by 4 kilometers. Enhanced backscattering fibers were proposed by Hendrik in 2018 and basically are very similar to the concept of FBG's fibers. And they provide a loss of 0.7 dB per kilometer. So they can actually extend the distance over which sensing occurs by 24 kilometers. So using this approach means that we can work, instead of over 45 kilometers of fibers, over 70 kilometers of fibers. And you can see that it's a big benefit when you want to do when you want to monitor the environment, because once you go underwater, you have a single access, and having the possibility to monitor hundreds of kilometers rather than 45 makes a huge difference. In our approach, we use a femtosecond laser, which is the schematic of which is reported here. So we have a femtosecond laser which goes through a frequency doubling unit, the BBO here, and the green light then goes through polarization maintaining, polarization selection, optical components that are then is then focused onto a fiber, which is placed down here. By selecting the intensity and the repetition rate appropriately, we can induce changes in the silica, in the material of the fiber. According to this graph reports what sort of effects we have according to the duration of the laser pass that we use. And as you can see, while at long pass durations, we have mostly thermal shock wave effects, at short durations, we have carrier excitation and thermalization. So we can have structural changes which are not induced by the thermal effect, and therefore are focused only where we focus light. Even better, when the number of photons, where the intensity is high enough for the number of photons to be sufficient to excite electrons in the conduction band. And this is what we have basically observed. We can induce refractive index changes in glass, like you've seen in the left, on the left side, in silica, in borosilicate, in fluoride glasses. But we can also induce gratings, like you can see on the top right here. So these are nano gratings. They are gratings, the pitch of which is much smaller than the beam that we use. And if the intensity is really high enough, we can make bubbles, we can make voids inside the material. So by tailoring the intensity right, we can actually nanostructure the fiber and increase the back reflected intensity by 20 dBs. So this is a threshold fiber that we manufacture and we splice at the end of our fiber. The OTDR intensity, as you can see, decreases until when it reaches the noise level. And when our fiber is spliced, it has again an increase of 20 dB. So in this case, only few hundred meters of fiber were spliced. But in principle, this can be used to extend even further the range. And the interesting part of that is that when the loss was measured using the cut bag, this provided an induced average loss of 0.1 dB per kilometer, which is very small indeed. We repeated the same measurement on a different type of fiber, and we still obtain 0.1 dB per kilometer. So we have a signal enhancement of 20 dBs and an attenuation of 0.1 dB per kilometer. This means that actually our fiber can extend the range by 66 kilometers. In other words, using single access, and our fiber after a normal telecom fiber, we can detect vibrations at 110 kilometers away. So we decided to go even further and launch our pulse together with Raman amplification. And we basically monitored vibrations as far as 150 kilometers. But the benefit of this approach is that it has a signal to ratio which is really small. Our colleague in US at the Naval Research Lab have used our fiber to monitor what is the effect of these structures on the acoustic signal. And here you see on the bottom the relay signal from a normal telecom fiber, followed by a signal coming from our fibers. As you can see, there are enhancements wherever we wrote the reflectors. And what is interesting is that when they monitor and they compared the signal coming from a telecom fiber, here in dash red in the left graph, and the signal coming from our fiber, they saw an enhancement up to 30 dBs of the signal to noise ratio for frequencies between 10 and in excess of 10,000 hertz. So in other words, our fiber can decrease the noise level that is the limitation for long distance measurements. We use these we commercialize this fiber through a spin-off that we just set up, which is called SFOS. Applications of these are not only for environments. Typically, they are used around airports to monitor intrusion, pipelines, but also for tsunamis, and that is where our main application is in Japan. Earthquakes is under investigation at the moment, and the idea is actually to use this for landslides, simply because the long distance monitoring capabilities allow us to detect small ground noises over a very long distance. Now, as I mentioned earlier on, there is the distance issue, the fact that 45 kilometers is what distributed optical fiber sensing systems at the moment can monitor. We use our fiber together with amplification, and we demonstrated that actually with a single access, it is possible to monitor 150 kilometers plus from a single location. So this means that having two locations 300 kilometers apart allows us to monitor the whole area that is between the two locations. And you see the benefit of this, because this means that you can have few stations that allow to monitor basically a single country. Here we compared the results coming from the DAS system on the right, so our optical fiber distributed sensing system, together with conventional geophones. And as you can see, they basically provide the same results. They all detected the P waves and the reflected P waves and the S waves. That are particular type of acoustic waves propagating into the ground. And there is a closer resemblance with the horizontal one. And this is basically what we would expect, because optical fibers tend to detect strain only along the longitudinal direction. And indeed, when we compare the signals between the horizontal geophone and the vertical geophone, we see that our optical fiber unit has basically the same trace as the horizontal one, while the vertical one is quite different. So in conclusion, I hope to have shown that distributed sensing could be a potentially cheap solution for environmental monitoring. And this is particularly true if our new fiber that was developed in Southampton is used, because this enhances reflectivity by 20 dBs and induces an attenuation of only 0.1 dB per kilometer, meaning that it's possible to monitor 150 kilometers from a single location. Thank you very much. Is there any question?
Thank you so much, Professor Gilberto. Very interesting talk, something new to me. It's a very interesting application. We hope there are questions from the audience. I only can hope for it. Any question from the audience to Professor Gilberto? Very interesting idea using distributed sensing. I think acoustic sensing. Very interesting. Any question? Professor Ken, you would like to ask a question? We have one question from our member, Professor Ken Grattan.
Yes, thanks, Gilberto. Very interesting talk, and it's really good that you have extended the range. What do you think the limit is? Okay, you mentioned 150 kilometers. Do you think you can go much further? Are there tricks that you can play to go even further? Extending the range.
Yes, actually there are, and that is what we are trying to do now. Because clearly one of the limitations, well, the biggest limitation is what sort of signal you get back. So at the moment we provide only 20 dB enhancement in the backscattered signal, but we achieved in the lab up to 50 dB enhancement. So this means that reproducing that in a fiber that can be deployed means extending even further the range. So we would have another probably 50 kilometers in addition to what we have. There are some tricks that can be used for the amplification. So using EDFA, fiber with Raman amplification and so on. So we believe that we can exceed 200 kilometers. I think if you don't use repeaters, it's going to be more difficult.
Good. Okay. Thank you very much. It sounds very promising.
I think Luigi, then Gino has also a question.
Yes, Gilberto. Just a curiosity. You talked about very long fibers that have to be manufactured with the use of femtosecond lasers, if I understood well. How much does it cost? I mean, the cost per kilometer of this new kind of fibers.
So I don't have a simple answer to that, okay? Because it depends on what sort of fiber you you use. So, for example, submarine fibers tend to be cheaper to process than terrestrial fibers. So dispersion shifted tend to be a bit more complex to process than the normal telecom fibers. And depends on how frequently you want these reflectors to be, because there is a cost per reflector. So if you want to have a reflector every 100 meters, like in the case of earthquake monitoring, that is reasonably cheap. Reasonably cheap, meaning that it can cost probably in the region of £100 per kilometer. This is still significantly cheaper than what is sold, for example, by FBG fibers. So they cost about twice as much. Or the continuous grating fibers, those are 10 times larger. But ultimately it depends on the specifications of the fiber that you want. So if you want to have a fiber for earthquake monitoring, I think probably £100 per kilometer is probably a rough idea of what you would spend.
Thank you, Gilberto.
That's okay.
Any more question? If there's no more question, I just don't know how to use the Google Meet to show to thank you with a clap of hand so that you can have some sound on the clap of hand. But anyhow, I will clap here. And thank you so much, Professor Gilberto, for the time. Early morning to stay awake and to give a talk. We do really appreciate your contribution. Thank you so much. So
thank you, Prof.
We'll break for lunch. We will meet up again at 2 o'clock with another interesting talk by Professor Luigi Sani from Italy. I hope that everybody should attend. It's a very interesting talk by one of our invited speakers. Thank you very much. I will see you after lunch about 2 o'clock. Bye-bye. Take care.
Yeah.
So you will take over, okay?
All right. Okay. Thank you, boss. Assalamualaikum and good evening. Good afternoon. Prof. Harith? Good afternoon. Prof. Lugi. How are you, Prof?
Yes, here I am.
How are you?
Fine.
Okay.
Thank you.
Yeah, it's a pleasure to have you here.
You're welcome.
Right. Okay. Welcome, everyone, to this afternoon session. We will have Prof. Luigi Zeni from University of Campania Luigi Vanvitelli, Italy. I hope that I pronounced it correctly, Prof. Luigi.
Yes, correct.
Yeah, Prof. Luigi Zeni is a full professor in electronics and photonics at University of Campania Luigi Vanvitelli, president of the Research Consortium on Advanced Remote Sensing System, which another call is CORISTA, member of the Board of Directors of University of Campania Luigi Vanvitelli, and Rector's Delegate for Technology Transfer Activities. He had been a national coordinator of PRIN projects funded by the Italian Ministry of University and Research, MIUR, in 2000 and 2005. He is also a reviewer for PRIN projects, industrial research projects, and European Research Council projects, as well as being a member of the editorial boards of Sensors and Transducers journals and Sensors. Moreover, he is also the author of about 175 papers in international journals, more than 150 publications at international conference and 12 patents. And I would like to welcome Prof. Prof. Luigi Zeni with the keynote presentation with the title of Surface Plasma Resonance in Polymer Optical Fibers, a versatile optical sensing platform for point-of-core analysis. I would like to welcome Prof. Luigi Zeni.
Thank you, Rosalina, for your nice introduction. Good afternoon, everyone, and I hope you enjoyed your lunch. I just finished my breakfast because in Italy it is 8 o'clock in the morning. Now I try to share my screen. I hope I succeed. Let me check. Can you see my screen?
Yes, Prof.
Can you?
Yes, we can see
Okay,
your
thank
screen.
you. Okay. Now it's in the full screen mode. Okay, so as as told before, I will talk about the surface plasma resonance in polymer optical fiber, seen as a versatile optical sensing platform for point-of-care analysis. Before starting with the devices, I would like to point out what we mean by point-of-care analysis in medical diagnostics. So usually, as you know, when specific analysis have to be carried out, they usually draw blood samples or other fluid from the patients. Then these are brought to outer lab. So this is the usual procedures. And then they are analyzed. Then the results are sent back to the doctor, and in this way he can adjust the therapy, let's say. This is a usually very long procedure and lengthy procedure. But when the results need to be available promptly so that decisions can be quickly made, let's say in intensive care units, on the basis of these results, the so-called point-of-care tests are called for. So point-of-care tests are tests that can be carried out just near the patient, and the results can be made available in very few minutes. This can allow the doctor to adjust the therapy in real time. And this is very important. And this is the direction toward we are moving nowadays. And in this framework, the final goal would be the possibility to shrink down an entire laboratory analysis, as you can see from this picture, on a chip. So made a multifunctional chip able to perform different kind of analysis in real time. Of course, we are pretty far from this goal, but nowadays, many sensing devices are going to be developed that are able at least to determine specific drugs, specific chemicals present in patient body fluids, and allow at least a partial real-time analysis. In this context, many kinds of sensors can be employed, but today's topic is on optical sensors, and as already discussed by the previous speakers, Aziz in particular, surface plasma resonance can be a useful tool to develop optical sensors that are able to perform this trick. So this is the outline of what we are going to discuss today, this afternoon. So I will briefly introduce surface plasma resonance and the localized surface plasma resonance. Then we talk about the possibility to make the sensors selective to specific substances, because this is a crucial point, let's say, because we need to detect a kind of substance and not others. So the selectivity of the sensors is a fundamental point. Then I will show you the the platform. The platform we are working on at our university, and I'll show you some application examples to medical care. Then in the last part, I will talk about an extension, let's say, an improvement of our platform that is based on gold nanogratings, and I'll show you how this platform can highly improve the sensitivity, so the detection limit can be greatly enhanced. And I'll show a few non-specific application examples, and then we will draw some conclusions. So, what are surface plasmons and surface plasmon resonance? You know that surface plasmon are coherent oscillation of electrons propagating in the interface between a dielectric medium and a thin metal film. You can see from this picture how this can be envisaged. You have a metal film. When you impinge on this metal film with an optical beam, if certain conditions are fulfilled, you can excite this electron wave oscillation that interacts with the outer medium, in this case, the dielectric sample in this picture. Yeah, you can see also the evanescent wave decay in both media. So this resonance comes out to be very sensitive to tiny change of refractive index of this dielectric medium. This means that if you look at the change of the resonance condition, you have a mean to measure this tiny change of the refractive index of the dielectric medium. How this can be implemented? From this picture, you see something like a prism and an optical beam launched at a specific angle. In fact, the classical detection scheme with the surface plasmon resonance is the one that involves the angle excitation, angle interrogation, let's say. And there are different commercially available devices, instruments that can be purchased on the market that implement this kind of interrogation system. And what we can do in this way, we just change the incidence angle in this way, and when an interaction takes place, so a change in the dielectric constant in the refractive index of this medium occurs, you can observe a shift in the resonance peak, because when the plasmon is excited, the reflected beam experiences a drop in the intensity because energy is transferred from the incident beam to the plasmon along the interface. And this is apparent in this picture. So we can just monitor the shift of the resonance angle to be able to detect the refractive index. Here you can see some examples. And here is also another kind of integrated devices that is from a US patent and dates back to 1997. So it is a very consolidated, let's say, technique to make sensors, to make optical sensors. And this occurs when a continuous metal film, in particular, usually gold is used. So this film, this one, is usually made of gold or silver, but usually gold in biosensing applications. But when the metal is not a continuous film, but is a nanostructured surface or an ensemble of nanoparticles or things like that. Anyway, whenever the surface is not uniform, but is nanostructured, you get another kind of phenomenon that is called localized surface plasma resonance, that behaves a little differently. I mean, the shift in the resonance may be different. And it usually also possible to interrogate this sensor or excite this resonance, not just by changing the incidence angle of a monochromatic light beam, but also to illuminate the device with a wide band light. And in this case, the resonance are excited at certain wavelengths, and these resonance wavelengths change when the refractive index of the dielectric medium change. So it is basically the same phenomenon, but the kind of interrogation is different. Let's say that from my point of view, the spectral interrogation is more versatile because it does not require any movements, any change of angles, and can be done in an easier way. Of course, the drawback is that in the detection scheme, you need a spectrometer. This in decades back was not a simple thing to do because spectrometer were huge devices, benchtop devices. But nowadays there are a lot of very, very small and cheap spectrometers that made the possibility to exploit the spectral interrogation a good chance. So this is as the sensor in general is concerned. I mean, either by angle interrogation with the classical commercially available instruments or by spectral interrogation, also talking about surface plasma resonance or localized surface plasma resonance. What we detect, as I said before, are just tiny changes in the refractive index of the medium. So this means that the sensors is not specific one. It's not specific one because the change are relative to the refractive index of the medium. What we need, of course, is not a specific sensor. We don't need a refractometer, but we need a sensor able to detect specific molecules, specific elements. Otherwise, it is useless for our applications. So, what is very important is to understand how we can make a sensor that is basically a refractometer, I mean a refractive index sensor, to make it suitable to detect specific molecules, so to be made useful for our purpose. In particular, in this case, we talk about the point of care analysis. This can be done, of course, in different ways, but basically what we need something, an element, to be deployed on the sensor surface, in particular on the gold metal, on the gold film. It's something that is able to specifically recognize and bind the element we are looking for. And it should also be negative to other elements. This can be done with this kind of receptor films. And this process is usually called the functionalization of the gold surface. So in this way, when the specific receptor binds, you see this change in the response. here you can see some possible schemes concerning this concept. In particular, the general scheme is the recognition element, the transduction system, and of course, the measurable signal that can be a current, a voltage, photon, frequency, and so on. And the recognition elements can be of two kinds, non-biological or biological. Okay. Non-biological means that are some chemical products, let's say. Biological means that we use biomolecules available from the natural processes. And the transduction can, of course, be of different kinds. Apart from the optical transduction by means of surface plasma resonance, you can use different kind of transduction. This is a cantilever beam that changes its resonance frequency when the specific element binds on its surface, and here you can measure the resonance frequency. It is a very old way of implementing this kind of devices. Or also electrochemical detection. I mean, this is there are some electrodes here, and when the selected molecules binds to the surface, you observe a change in the current and the voltage and so on. Of course, all these classical detection way do not have the advantage of optical detection that were well pointed out by Aziz this morning. So we stick with optical detection, in particular surface plasma resonance. What has been done, what you can find in the literature concerning the plasma resonance and optical fibers. Here you see an overview of many different situations that can be found in the literature when the optical fiber are micro-machined, are manipulated to let the evanescent field come out and interact with the metallic layers. So you can have the treatment on the tip of different kinds, a conic shape or a wedge shaped, or you can have fibers that are etched around to allow the field escape and interact with the metal, so generating the surface plasmons. There are very different possibilities. Here is a break grating. That is another possibility to excite surface plasma on the surface, and so on. Here you can see a detail of one of these devices. Okay, but what I will show you today is a specific kind of optical fiber device employed to excite and exploit surface plasma resonance. In particular, we will talk about an intrinsic sensor made in polymer optical fiber. Why polymer optical fiber? Because they are cheap and very easy to handle. So imagine that our goal is to realize a device that is very sensitive, very selective, and also cheap, so that it can be easily employed for point-of-care analysis, where you can't afford very complicated and costly devices. So we developed since, let's say, 10 years, maybe more, this kind of platform that is very, very simple. what we do is just take an optical fiber that is made of PMMA. Okay, it's a very huge one. It's a 980 micron core and a very thin 10 micron thick cladding. And we just include this fiber in a resin block, and we grind the surface so that removing the cladding a part of the core. Okay, this gives out the so-called D-shaped fiber. And on this part, on the flat part of the fiber, we deposit a photoresist buffer that has a refractive index a little higher, so it allows the electric field to be extracted more easily from the fiber, from the optical fiber. And then the gold film, and then the other steps, functionalization and so on. Here you can see the basic devices. This is a 1 cent. No, it's a 1 euro coin. So it's a very small device and a very cheap device. So starting from this basic device, we exploit spectral interrogation. We exploit spectral interrogation by means of a white light source and a compact spectrometer. You can see the overall size of the object. This is just a holder allowing to easily couple the fiber, the input and output fiber, to the light source and to the spectrometer. And it can be also interrogated by means of a Raspberry Pi or Arduino configuration, using just a LED and photodetector instead of the white light source. Anyway, this is these are the different possibilities. We also exploited an interesting configuration where instead of the white light source, we use the fluorescent optical fiber as the light source. It means that you don't need any more devices, just a loop of fluorescent fiber that is illuminated by the ambient light and emits in the red and can be used to excite the surface Planck resonance in this device. Okay, let's go on because the time is running. Okay, so what about the receptors we employ with this kind of devices to make it sensitive to specific substances? We basically focused on the two of these kind of receptors, in particular bioreceptors and synthetic receptors. I'll show you examples of both cases. As bioreceptors are concerned, we usually exploit antigen-antibody complex that, as you know, is a very specific binding. I mean that the antibody binds specific antigen and no other substances. Those is a kind of a lock and key situation that makes the sensors very specific. And another possibility we exploited is to use the so-called aptamers that are just short DNA strands. And as you know, for the complementarity of the DNA chain, you can use this to detect specific substances. And on the other hand, we use also the so-called biomimetic receptors. By biomimetic, we mean that they mimic the nature, the bioresponse, but are actually polymers. And in this case, we talk about molecular imprinted polymers, or MIPs. What are MIPs? Are synthetic polymers that can be, let's say, constructed around the target molecule in this way. Okay. Then the target molecule or template is washed out, is removed. So leaving in the polymer specific binding sites that are very, very selective for the target molecule. So we mimic something like an antigen-antibody process, but with the advantage of being a polymer, so it's much more stable, is a very high off-the-shelf shelf life with respect to the biomolecules that are very fragile. They require particular care when manipulated. Okay, so is what we exploit for our application. Now I'll show you a few results on different medical applications, as I said. We start with the celiac disease. The celiac disease, you know, is affects a lot of people, and these people have to be monitored. In particular, in this case, we developed a biosensor using transglutaminase, so an antigen and antibody reaction specific for celiac disease. This is the sensor, the basic devices, the basic platform is the one I showed you before. So there is the photoresist buffer, the gold layer, the functionalization with the antibodies, and it works in a water solution. This was published in 2013, this first one. And here you can see how the resonance wavelength of the plasmon changes. Okay, you see when the concentration of the transglutaminase increases. This is what we read on the spectrometer, the resonance curves, and the shift is a red shift in this case. And what we were able to reach was the concentration in the nanomolar range. So it's a very interesting result. And as the selectivity is concerned, here you can see the response when there is no functionalization for the specific antibody. So the sensor is also very, very selective. Another interesting application was made using aptamers. In particular, we used aptamers able to detect the so-called vascular endothelial growth factor, that is a well-known cancer biomarker. And also in this case, using aptamers with a special functionalization procedure. Here you can see on the left just what happens to the resonance wavelength before and after the functionalization. Of course, there is a shift because functionalization implies the binding of the aptamers on the surface, and this changes the refractive index. So we have a pre-shift, let's say. Then this shift increases when, as you can see here, when a growing concentration of the detected, of the searched for molecules are added, okay? In this case, the limit of detection was 0.8 nanomolar. So in this case, it's very interesting. Another application with apta sensors, I mean with the aptamers as the detecting mean, was for thrombin detection. Also in this case, you can see that when properly functionalized, the sensor is able to respond to the increasing concentration of thrombin, and it is also insensitive to other molecules. So the selectivity analysis shows no resonance shift, while here there is a definite resonance shift. In this case, the limit of detection was 1.6 nanomolar. Again, another application where antigen antibodies complexes were used concerns the detection of infliximab, that is a therapeutic antibody used to treat chronic inflammatory diseases. That is very important for medical diagnostics. Also, in this case, you can see that when properly functionalized, the sensor gives a definite response in the wavelength shift, resonance wavelength shift, where when it is not properly functionalized, there is no shift at all. In this case, the limit of detection was 74 nanograms per milliliter. This is a very recent result published in 2020. Then, when the pandemic break out last year, we tried to take advantage of our sensors also to detect the variants of COVID-2. In this case, we used the biomimetic receptors. In particular, we synthesized a MIP layer specific for the spike protein of the COVID virus. And we tested on some patients, and you can see here some of the results. That in particular, on the left side, these are the results achieved on positive swabs in a physiological medium at different dilutions. While on the right, you can see similar results, but achieved with positive swabs in the UTM, that means universal transfer medium, if I'm not wrong. That is a particular solution used to transport the samples from the nasal swab and to process by means of regular procedures, that is PCR, I think everyone knows this because we are talking about this kind of things since more than 1 year. And here you can see the comparison, and in this case we have a very high detection rate for positive swabs in both cases. So also for swabs in a physiological medium and for swabs in UTM. The only aspect concerning UTM is that the dilution is different because it's a different medium. This means that with this sensor you can detect the presence of the SARS-CoV-2 virus in a few minutes, because all the measurement procedures takes, let's say, 5 minutes. So you don't have to go in the lab to amplify the nucleic acid of the virus and go on. And also on this line of argument, we also developed another sensor for detection, in this case, of the spike protein, but using not the biomimetic polymer, but DNA strands. I mean, an APTA sensor, similar to the one we discussed about a few minutes ago. And also in this case, we were able to detect with a good sensitivity the presence of the spike protein of the spike protein. I have to say that in this case, we did not test this sensor with real values, but just with the protein. And I have also to say that this sensor is more fragile from a point of view of storage and so on, because as I told you, in this case, we use aptamers that are not as stable as the synthetic polymers. And finally, it is another application concerning the detection of pancreatic amylase in surgically placed drain effluent. And also in this case, we use the antigen antibody detection scheme, reaching a detection of 0.48 unit per liter. And here you can see the shift on the resonance and the interference analysis. Okay, now if I have a few more minutes, I would like to briefly talk about another devices that we are developing in our lab that is not as simple as the previous one, because concerns the use of nanostructures, in particular gold nanogratings, but it is an extrinsic sensor, because the light comes out from the optical fiber, the plastic optic fiber, and then is coupled back in the fiber again. So it's an extrinsic optical fiber sensor. And in this case, we exploit a localized surface plasma resonance, because we have nanostructures, nanogratings. And this is a chip made of PMMA, so the same material as the optical fiber, but it is covered with the gold film, and then a nano-patterned exploiting electron beam lithography. You can see the procedure that we perform in our labs. And then we have this kind of device where the gold layer is all over the grating. This is an SEM picture of the device itself. And in this case, we have a very small sensitive area. Consider that the classical sensor we showed before is a sensitive area of about 10 square millimeters. That is the portion of the fiber that is made D-shaped, flat. In this case, we have a very small area. It's about 1 square millimeter. So it means that you can also use reduce the quantity of analytes. But this is a special holder that we designed and realized by 3D printing to hold the chip and also hold the reference, let's say. And the illumination is made by the white lamp, and the detection always with the portable low-cost spectrometers. And just to understand if this was suitable, we tested with a special functionalization made with an imprinted, a molecular imprinted layer, so a biomimetic detection layer, and we tested for the BSA, that is bovine cerebral albumin. It's a protein that we mostly used for tests and so on. And we devised this kind of response. But what is very interesting is that this kind of detection, I mean exploiting nanograting and so localized surface plasma resonance, allows to reach a detection limit of 37 picomoles, compared with the same devices but made with the D-shaped fiber and with the surface plasma resonance instead of localized surface plasma resonance. Tested with the same BSA protein, we had at 0.37 micromole, Okay, and the detection range between 0.37 and 6.5 micromole. In this case, with the nano grating, we achieve a 37 pico, and this detection range. What does it mean? That the two devices cover different ranges. So if you need a very high sensitivity, so a very low detection limit, you can use the gold nano grating MIP based. Otherwise, you can use the classical SPR plastic optical fiber MIP. And in between, you can see also different devices that can be found in the literature containing the same detection of BSA, okay, bovine serum albumin, with devices. And as you can see, this configuration is pretty good. It's pretty good if you consider the detection limit and the detection range. Okay. So that's almost all I wanted to talk to you about. So in conclusions, what we showed that a small size optical biosensors for high sensitivity and high selectivity detection of several substances can be realized with a simple, low cost and easy to manufacture device based on plastic optical fibers. The potential in detecting and treating a disease or measuring components in biological fluids makes them excellent candidates for point-of-care analysis, because there you need a quick and cheap devices. All these sensors are low cost and they are also suitable for mass production and can be easily connected to the internet, so allowing an Internet of Things approach. And finally, the gold nano grating is very promising and will be exploited for medical diagnostics in the next future. Thank you very much for your attention.
Thank you so much, Prof. Luigi, for very interesting, impressive, and full of information presentation. Yeah, I would like to invite any question from the members of floors. Yeah, yes, a question from Dr. Fairuz or Mr. Fairuz?
Hello, Prof. Zeni.
Hello.
Thank you very much for the presentation. Just one, you were working with biosensors, in particular the SARS-CoV. Do you collaborate with virologists, or is there any precaution that, or anything that you can say about if you were working with that kind of sensor in terms of safety, security, and whatnot?
Yes, of course, we collaborated with the hospital personnel and all the safety procedures were followed. And there was the personnel from the hospital that made available the samples from nasopharyngeal swabs from a patient that was under care in the intensive care unit.
Okay, thank you.
You're welcome.
Thank you, Dr. Fairuz. Anyone else? Any question? Yes, Prof. Gilberto?
Yeah, I was wondering how cheap can this become? Because if you have a look at the moment, the hospital pays about 50 euro cent per test. Do you think that in terms of cost, you can go down to that level?
Yes, we are working toward this because our a new spin-off company, I didn't show it, but I can, okay. Here is the more sense that a newborn spin-off company that is working toward the mass production of these sensors, and specifically also for COVID, with ST Microelectronics, that is a well-known company working in the microelectronic field, a multinational. And this spin-off company is working toward this. And the idea is to realize a a much cheaper device compared to the actual costs of the COVID tests, of course.
Thank you.
You're welcome.
Prof. Ken?
Yes.
Yeah, thank you, Luigi. Very, very interesting talk, covering a lot. One question really in relation to the use of sensors like this in dirty water, where you might have particulates and other things. What do you think is the solution to protect sensors like this, where you don't have the clean laboratory situation, which is the sort of situation that is ideal for using these sensors?
Yes, this is a crucial point, of course. In our case, the results I showed you are concerning medical applications. So the fluids are body fluids that sometimes have to be diluted, but usually are not filtered, because the specificity of the sensing layer is very high, and it just concerns the surface of the sensor. So the so-called bulk effect in this case are not present. Of course, if you imagine that the similar sensors can be used for water analysis, environmental monitoring, and so on, and in the water there are a lot of pollutants and dirty things, particulates, and so on. Of course, the water should be filtered in advance. Otherwise, it sticks to the sensor surface and it will not work anymore. That's for sure.
I think I'm just wondering if you can create a sort of a filter within the sensor itself, so that you could have the sensor inside some sort of filter type of housing, and perhaps in that way to protect the sensor.
Yes, of course, you can adopt a microfluidic device that contains also filtering units. So that you can sample the water, pass it through the filtering unit, and then send it to the sensor surface. Of course, the filters have to be cleaned periodically, depends on the frequency of use and so on.
But at least cleaning filters is much easier than cleaning sensors.
Of course. If the sensor surface gets dirty, you have to waste it.
Yes. Thank you very much.
You're welcome, Ken.
Thank you, Prof. Luigi, for your evening presentation. Thank you so much again.
Thank you.
Okay, thank you.
Okay, I removed my screen sharing. I hope I'll be able to. Okay. No, okay, I did it. Okay, right. So thank you very much again.
Thank you, Prof. Thank you so much.
Bye-bye.
Okay, bye-bye.
Bye.
Prof. Rizal, your mic is not on.
Hello, is it my turn?
Oh, sorry. My microphone. Okay. Right. Okay, now we are ready for the next presentation. Right. Okay, wait. Let me open the details. Right. Okay, we will have another presentation by Yap. Is it? Yap? Yes, Yap. How are you, Yap?
Yeah, good.
Long time no see you, Yap.
Yes.
Yes, okay.
It's been really quite some time. Yeah.
Oh, yeah. Okay, we have another presenter, under supervision of Dr. Chong and Prof. Harith. And you will present a title with graphene oxide-based optical sensor for water content measurement in alcohol. Please welcome, Mr. Yap.
Right. Thank you, everybody. So I'm really glad to join here. So currently, I'm attached to Sarawak University, Malaysia. Though we are yet to celebrate. We are almost celebrating our 10-year anniversary in Malaysia here, but yet to reach that. The research, especially on optics and photonics, is still rather new. Relatively starting at a humble beginning at Malaysia campus here. So here am I to present a humble little work that I myself have done with the Photonics Research Centre under a project leader. So because later on, today it's still my working day, I will have an appointment to attend. So I have recorded my presentation in a video form. Henceforth, I will actually share the video. Please do not worry, after the video ends, I will still be here for a little while to take any inquiry or any questions or any critical feedbacks or comments are most welcome. So I will start sharing now. Okay. Okay, just a minute. So can anyone see the player? The player is visible?
Yes.
Okay, right. So I will start playing now.
Yes.
This is a collaborative work on graphene oxide optical sensor for water content measurement in alcohol by the Photonics Research Centre of the University of Malaya and Sarawak University, Malaysia. So the main cast here is graphene oxide itself. So this two-dimensional nanomaterial, I believe it's no more unfamiliar to all researchers and scientists, especially those in the material science, researching in carbon-related materials. So this page here is mainly just to highlight only a few of the important peculiar characteristics of graphene oxide, tailoring it to our optoelectronics and photonics application here. So namely, graphene oxide is different from graphene because graphene oxide has functional groups such as the oxygen and the hydroxyl groups here and others. So that makes it to have a band gap, unlike graphene that exists as zero band gap. So due to this, graphene oxide has tunable band gap and it is highly soluble in water, unlike graphene. So it is soluble only in organic solvents, but graphene oxide has more choices whereby water as a universal solvent is able to disperse graphene oxide well. And in the process of making or synthesizing graphene, usually graphene oxide will appear first if we use graphite as the raw material. So we say that it serves as a precursor for graphene. And once again, for photonics, especially in ultra-fast fiber laser, ultra-fast laser application, it exhibits saturable absorption properties, which is a non-linear optical properties of the material here. But the highlight here is that our work here truly exploit the anisotropic properties of graphene oxide. So now what is actually anisotropic properties? That means the changing or the variation in generally the physical, or once again, more specifically to our application here, is the optical properties of the material, namely graphene oxide itself, depending on the direction of propagation or the orientation of the light that is incident on the graphene oxide itself here. So this is what we call anisotropic properties. So seeing that the graphene oxide will see actually the incoming light differently when the polarization state of light is tuned and controlled. So anisotropic properties of graphene oxide there were a few reports on that. So one of it is that it was reported that it has a complex dielectric function due to this special property reported by one of the previous work done by other research group. And we have also actually utilized this complex dielectric function to realize a fact that graphene oxide could enable high loss transmission for electromagnetic light, electromagnetic wave, a high loss transmission for transverse electric mode, and the other way around for the transverse magnetic mode. And we have also some similar and related work done on exploiting the anisotropic properties here. But in this work here, so we've extend a little bit to make it in a more real application, as in this water content in alcohol sensing properties. So this is a proposed sensor structure here. Okay, so this is the main structure of the waveguide. So we have a light source here. So we use a C-band light source. So this C-band light source is passed through a PC controller here, which is polarization controller actually. So this PC here is mainly to tune the polarization state of the light so that any light that will pass into the waveguide is transverse electric mode. So the transverse electric mode here mainly is set by the PC itself, and it has been verified by using a polarimeter. And the graphene oxide, okay, so we have applied it onto the waveguide here, which is at the main channel. So the dimension of the graphene oxide film, GOF, is being shown at this part here. So we have verified this also using this X-ray diffraction and also this transmission electron microscopy. Okay, so after everything was set up, and this is connected to a power meter. So this is where we apply drops of water content in alcohol that is dilute with different water volume percentage. So the alcohol that we use here, it is easily available in our place here, which is IPA, isopropyl alcohol. And lastly, not to mention about this power meter here. This power meter here is mainly to monitor and to measure the TE mode propagation loss. Okay, because the light that we are all using here, it's incoming light into the waveguide with the graphene oxide film covered on it is in TE mode. So the power meter here is to monitor and to measure, evaluate the TE mode transmission, absorption, and loss. So we apply actually drops of water here, and we actually analyze the drying profile of the water in the graphene oxide itself here. So a very quick. Now this page here shows generally the results of our findings here. So we measure the drying time. So we call it here the drying profile of the water when it was applied onto the proposed sensor itself. So this is the first one that you are seeing here. So at first you will see that for very low water content, for instance, 0.3 or up to 17% of water content in alcohol in IPA. So the drying profile is rather kind of like interesting here, because it doesn't actually show a very significant change in the transmitted power as compared to the later part here. So here we always look at it relatively. So it seems like the 25% and 30% of water content measurement, it's kind of like have a greater transmitted power compared to the low water content. So we have actually proposed that, at this section here, because the water molecules, okay, so form rather complex bonding with the alcohol, with IPA itself here, then the larger alcohol molecules are actually unable to permeate. So larger here, again, when we compare to water molecules. So the complex bonding was formed. So it makes that the water molecules are not able to permeate the graphene oxide layer. Now for the later part here, you can see that the maximum transmitted power is kind of like greater. So the response has increased for higher water content. So at this part here, we believe that the alcohol actually is drying faster than water. So when the alcohol dries, that means the bonding between the water molecule and the alcohol could be missing, non-existing anymore. So the water molecules were kind of like liberated, okay, from the bonding with alcohol. So therefore, the water can intercalate, okay, in between the graphene oxide layers. So the TE mode of the light will be able to go through more on the graphene oxide layer without much absorption. Henceforth, you see a greater transmitted power. So we have also measured the maximum transmitted power, found it to be for every volume percent change is about 0.75 dB. So now this first part of the drying profile here shows water content up to 30%. For more than 30%, up to 100%. So you can see that here 100% is pure water. I mean, when you say 100% water, that means it's a pure water anymore. So we can see that the threshold here plays kind of like give a different results compared to the first one here. So you see that it's almost an instantaneous response. Okay, for water content more than 30% or 30% and above here. So we believe that this part here is due to the suppression of the TE mode absorption. That means now the TE mode, which is kind of like parallel in the direction of the GO, the graphene oxide is now, the absorption is less. So this enables more TE, more power of the TE mode light to go through, henceforth the transmitted power actually increase. So this actually also comes from the change in the graphene oxide's dielectric properties, has been reported by some other works here. So it was believed that at this stage here, the water permeates into the graphene oxide, so interacting with the oxygen groups. So the intercalation of water molecules in between graphene oxide layer plays a very important role in giving or displaying the results that is being shown here. So for instance, for 100% water, you can see that the drying time is relatively longer compared to the others, which is of a lower water content. So this is just, I mean, the results, okay, a very raw part of the results that we obtain. So this is a summary of the conclusions. So we found that the less than 30% volume percent for the water content, the maximum transmitted power increases linearly. And for water content of greater than 30 volume percent, okay, the time taken for the restoration was found to increase also linearly. Okay, so no doubt this sensor, this work here can be further improved. So probably we need better calibration. So we need actually better control of the drying profile, the drying time, and more precise measurement on some of the optical sections, such as the transmitted power and many more to come. But we would say that this proposed sensor actually has a huge potential for real-time and in-situ water content measurement and monitoring for any solution. So in this case here, alcohol solution that has water content. So with this, I'd like to say a big thank you for your attention.
Okay, thank you, Dr. Yap, for your presentation.
Thank you.
Okay, I would like to invite any question from members of the floor. Any question? You can raise your hands. No question? Any question? No? Okay, I would like to ask one question, Dr. Yap.
Yes, please.
How did you fabricate graphene? How do you manage, how you fabricate and you ensure that you will have a very standardized, homogeneous, thin layer on your substrate?
Okay, so the graphene oxide is fabricated, okay, using just a common chemical method. So what we did is that we have tried many times, okay, so yeah, this is not reported in the presentation. We have tried many times that we use a micro pipette, okay, sorry, yeah. Micro pipette to pipette, yeah. So to just drop cut very standard, very slowly, not too fast, not too slow. Yeah, it's rather subtle here to say this, onto the substrate itself. And then we observe it many times using the, the microscope to ensure that, yeah, we do not actually have a very standard way, like, an empirical way to actually give a kind of like, or if I do it this way, I will definitely get 1 nanometer thick. So it's by a drop casting method And I believe the method here, we are quite confident that if we do it at the right way using the proper micropipette and the 1 microliter of drop, for example, it will more or less give you the thickness that we want within the range of the acceptance of the uncertainty. Yeah.
All right. Okay. Thank you so much for joining us this afternoon, Dr. Yap.
Thank you. Thank you.
Okay. Thank you.
Thanks.
Thank you. Yeah, we have next presentation by Waldo. Is it Waldo?
Wing.
Wing. Okay.
Yeah.
Okay. Okay. We here. Right. We have another presentation with a title called Label-Free Surface Plasma Resonance Fiber Grating Biosensor for Hand, Foot, Mouth Disease, in bracket EVA71 detection by Mr. Ui Cheong Weng. Am I right?
Yes.
Yes. Okay.
Yes.
All right. I will welcome you for your presentation.
All right. Let me share this windows.
Okay.
Can everyone see?
Yes. Yeah, we can see.
Is it too small?
Oh, yes. Yes, it's too small.
So let me. Wait me for a second.
Right, okay.
Can everyone see the slide?
Yes. Yes, I can see.
Okay. Sorry, my camera is spoiled already, so I cannot. You guys cannot see me. So I will start my presentation with my slide. Okay.
Yes, please.
Okay. So hi everyone. SPR TFPG, surface plasmon tilted fiber grating, is also known as gold-coated TFPGs, and they are known for their surface plasmon rational properties and ultra-high sensitivity to various liquid measurements and biochemical substance. So in general practice of the biosensing using the TFPG sensors, a standard baseline solution is used as their reference solutions, and the acquired measurement signals is actually from the test analyte, and is used to compare against a reference signal which measuring using the reference solutions that stated just now. But we find that this method might be vulnerable to the reflected index perturbations in the bulk mediums. Hence, we are suggesting a different approach to reduce the influence of global reflecting index noise on the sensors. So during the presentations, we will introduce briefly about what is the SPR TFPG sensors. And lastly, we will talk about, we will demonstrate the SPR TFPG biosensor for virus detections on the EVA71 virus. So nearly every commercial available SPR instruments that use a detection scheme called the Crashman configurations. Crashman configuration is the earliest and well-established SPR models based on the Prism couplings. In this setup, the light source passes through the prism will be reflected off the backside surface and into the detectors. At a certain incident angles known as the rational angles, the light is absorbed by the electrons in the metal films, causing them to resonate. These oscillating electrons are also known as surface plasmon and is sensitive to surrounding environments. So this will result in an intensity loss in the reflected beam.
Yes. Sorry for disturbing you.
Yes.
Your slides are not moving.
Oh, sorry.
Yeah.
Let me check. How is it now? All right. So I continue. Okay. So basically, once the SPR occurs, it will result in an intensity loss in the reflected curve. As you can see, there's a dip there. The shape and the location of the SPR dip can then be used to convey the information about the sensor surface. So the propagation constant of the surface plasmon is very sensitive to reflective index variations of the outer mediums at the surface of the metal films. So let's go to TFPG. Tilted fiber break grating is actually a FPG, the fiber break grating FPG with tilted grating planes. The TFPG stands out by enhancement of resonance of backward propagating cladding modes, which have a strong interaction with outer medium of the fibers. So we can observe here, there is a series of dip in the optical powers that in the transmitter spectrums. By depositing a very thin gold film, we are able to achieve the SPR effect with these cladding modes coupled with a free electron in the thin gold films. So when the fiber is coated with gold thin films, the working mechanism is quite similar with the Crashman configurations. The enhanced cladding modes by the tilted grating able to achieve SPR, and when specific group of the cladding mode with suitable effective reflective index that coincide with the surface plasmon wave, we can see the SPR when it will be very experience more loss than its neighbors. So as you can see, there is a SPR dips there, and therefore this cladding mode rational wavelength will provide a direct measurements on the effective reflective index of the SPR. So basically, this is the reflectometry for the SPR TFPG sensor that we use for the project. Sorry. So in terms of very large reflective index change, we use the SPR wavelength as the indicator to measure the reflective index change. As the reflective index increase, as you can see, the SPR tend to move toward the longer wavelength regions, and it's a linear relationship between the SPR wavelength and the reflective index change. So, but in virus detections, we are going to detect virus concentration that is very low. So we will having a very small reflective index change. So we will use another alternative by making the power variations of the particular sensitive SPR mode as our indicators. We will choose the most sensitive SPR wavelength and measuring the power amplitude change of the particular wavelength. As you can see that when the reflective index increase, the selector cladding mode powers will decrease. and they behave in which is also linear regressions. So when applying this SPR TFBG to biosensing, the TFBG will be need to biofunctionalize with specific bioreceptors that has strong affinity towards your targets. So we will need an intermediate layers for binding these bioreceptors. In our case, we will bind our antibody proteins that used to detect they're used to capture the targeted virus on the fibers. The intermediate layers used in our work is known as self-assembled monolayers, in a short form SAM. Usually we call it SAM, and it's covalent immobilizations that have strong covalent linkage between the proteins and the sensor surface. So the choice of your intermediate layers depends on your available functional groups in your bioreceptors. In our case, our proteins and the sensor surface. So there is different groups of intermediate layers that you can choose, like hydroxyl group, carboxyl group, or amine groups. So this is the brief procedure for our biofunctionalization in our projects. Firstly, the SAM that we use having the functional groups of carboxyl group. And it is required to be activated. As you can see, the activate process is activated using the NHS and WSC solutions. And after the activation, you just need to dip the sensor into the antibody solution. In our case, we're using the monoclonal antibodies for EVS71's virus. After that, once the antibody immobilization is done, we will need to dip the sensor into a blocking solutions, which is to aim to prevent the unnecessary binding error in the measurements later. So basically, this is the experimental setup in our project. The selected SPR mode has shown in the response to the test analyte that contain different virus concentrations. Due to the property of highly sensitive SPR TFBG towards the refractive index, the spectral signal that acquired in the virus solutions could be resulted from either the virus binding on the sensor surface or actually just the refractive index noise from the ambient mediums. Therefore, we will need to propose another additional methods by raising the surface after the the sensors after the detections in the virus solutions and immerse it into a clean baseline solutions. And we will make another measurements in the baseline solutions. So this is the result that we get for the detection on EVS71, which is our target virus. As you can see, there is a very small decrement in the signal, which allow us to make sure that the virus immobilization that is captured by our protein, antibody protein event is, we can make sure that the antibody virus immobilization happens there. So if there is no proteins receptor there, where it is just purely virus solution with that certain 10 to the power -3 refractive index, you will only get a signal change of around 0.1 dB. But if there is a virus capture events, you will get a higher power change. As you can see, there is a maximum of 0.6 dB change there. So this is how we make sure the virus immobilization actually occurs. So we did another control test to make sure where the SPR TFPG is not functionalized with any bioreceptor is actually bad SPR TFPG. We want to make sure when there is no virus taking issues on the fiber sensors. So the detector signal in the virus analyte, as you can see in the blue, is solely attributed to the change in the reflective index in different test analyte. Once we wash and we dip into the baseline solution in the orange in the PBS, which is the baseline solution, as you can see the signal, there is literally no signal change. So in terms of specific tests, we want to make sure that our antibodies, the monoclonal antibodies, have is selective to only detect the EVA71 virus. So the detector signal from the test analyte can be solely attributed to increasing solution reflecting index only due to the different viral concentration applies. Hence, as you can see, the huge drop in the baseline solution is actually similar to the result in control test. So we can say that the signal is actually solely comes from the reflective index, but there is no reflective index change that caused by the virus immobilization event. So all these findings have proven that it's important to our proposed protocols, which are very simple procedures that took just washing and dipping into a baseline solution and make a second measurements to make sure that there is no reflective index noise that contribute to the signal itself. So basically, the advantage of using the SPR TFPG is actually due to their small surface area of the biosensor, and we only require very small amount of antibody. And the sensor itself can be regenerated with, in our project, we use Piranha solutions and we recycle the sensor for about 3 to 5 times, and we're getting a similar result among all the tests. And the time is very short for getting a result, and it's very fast response. So that's all from me, and we want to thank that the impact-oriented interdisciplinary research grants that sponsor to our works, and that's all from me.
Okay, thank you so much, Mr. Oi. I would like to invite any question? Any question? Okay, no question. Right, okay, thank you so much, Mr. Oi, for your presentation this afternoon. Right, okay. Yeah, okay. Right now, we're going to invite for the next presentation. Before that, I would like to hand over this session to Dr. Nur Azrina. Okay. Screen is yours now, Dr. Nur Azrina. Thank you so much.
Oh, sorry. Okay. So, thank you, Dr. Rosalina. So, we continue our session with our next presenter. Our next presenter is Dr. Chong Soo Sin from School of Energy and Chemical Engineering, Zemin Universiti, Malaysia. The title of her presentation is Simulation Interfacial Behaviors of Fiber Optic Sensor for Soil Moisture Monitoring. So without further ado, I would like to welcome the presenter to deliver the presentation. So, Dr. Chong Susin, the screen is yours.
Hi, thanks, Dr. You share my screen. It seems like having some
We still cannot see your slide, Doctor.
is maybe a bit now.
I still cannot see your slide. Okay, okay. Okay.
Can see.
No, still cannot.
You still cannot.
Yes.
Guys, can you see?
Okay, now it's okay.
Now it's okay. So, is it the slide moving?
I can see your first slide.
Can you see, Doctor?
Yes. I can see your first slide. Can you move to second slide?
Okay, great. So is it possible I remain like this one or okay? How about this? You see the full screen? I apologize to taking you all so much. Can see?
Yes, we can see your slide.
Great, thank you very much. Because now I cannot read the comments, so I need your help in case so I'm the Chong Unit and chemical engineering. Actually, the next I would like to present is just a brief idea. This project will start in this 6 corporate from guys who have interest in this topic. So I'm going to present here is simulation and so soil moisture more on like this study in the agriculture in Malaysia. To Malaysia, we have some policy. Malaysia would like to encourage for the agriculture development in the
sorry. Maybe Dr. Chong have some problem with her internet connection. Can we go to our next presenter?
Yeah, okay.
Okay. So our next presenter is Mr. Ko Yozan from School of Engineering and Chemical Engineering, School of Energy and Chemical Engineering, Zamin University, Malaysia. The title of his presentation is Synthesis of Carbon-Based Quantum Dots Using Lemon Juice under Hydrothermal Method. So without further ado, I would like to welcome the presenter to deliver the presentation. So Mr. Ko Yozan, the screen is yours.
Thank you, Doctor. Do you see my slides?
Yes, we can see your slide.
Okay. So good afternoon, everyone. So I'm Johannes from Xiamen University, Malaysia, and I'll be presenting my paper titled The Synthesis of Carbon Content Dots Using Lemon Juice under the Hydrothermal Method. So this is the outline of my presentation, which comprises of research methodology, results and discussion, conclusion and recommendations, and finally, reference list. So to begin, this is a photo of quantum dots by honors. So quantum dots are miniature man-made semiconductor particles, which are smaller than 10 nanometers. They are usually applied in nanomedicine and bioimaging. However, when it decomposes, it emits toxic metals which harms the human body cells. Examples include cadmium-2 selenide and also lead-2 sulfide. So to encounter the disadvantage of the quantum dots, carbon quantum dots are introduced, which are nanocarbon materials extracted from natural resources and are normally smaller than 10 nanometers. And any carbohydrates with carbon, hydrogen, and oxygen ratio of 1 to 2 to 1 could be used to synthesize the carbon quantum dots. So although they are non-toxic and user-friendly, they exhibit lower emission and quantum yield compared to quantum dots. So this diagram on the right side shows the chemical structure of the carbon quantum dots. So next, the objective of my paper is mainly to synthesize the carbon quantum dots using lemon juice under the hydrothermal method. So why did I choose lemon juice? It is because lemon juice is rich in citric and ascorbic acid. Both citric and ascorbic acids have been used as carbon precursors in the preparation of carbon dots. Next, quantum yield percentage are enhanced by mixing onion juice. Furthermore, the relationship between the lemon-onion ratio and quantum yield percentage of synthesized carbon quantum dots are found. And finally, quantum yield percentage of synthesized carbon quantum dots is compared with previous studies. So next is my methodology. So technically, I did this in a laboratory during my bachelor's degree. So my samples are placed into an autoclave and heated in a vacuum oven at 120 degrees Celsius for around 3 hours. So after cooled to room temperature, the products are filtered by filter paper, 0.44 micron syringe filters, then 0.22 micron syringe filters. So the 5 samples of my study are are described so in this slide. So as you see, for the first mixture, I use only lemon juice, and then I change the ratio of the onion juice mixed with the pure lemon juice. After the samples are synthesized, they are sent to analysis for 3D measurements. So fluorescence spectrophotometer was used to find the excitation and emission wavelengths. Then the sample was sent for spectrum analysis, also using fluorescence spectrophotometer to find both internal and external quantum efficiency. And finally, the sample was then sent to infrared spectra, where Fourier transform infrared spectrophotometer was used to find the molecular structure and composition of the sample. And after the 3D measurements for pure lemon juice, the excitation peak was found at 470 nanometers, with emission peak between 535 nanometers to 575 nanometers. As for lemon onion mixture, the excitation peak was found at 485 nanometers, with emission peak between 550 nanometers to 590 nanometers. So the results show that the excitation wavelength is within visible wavelength range, which is between 400 nanometers to 800 nanometers, thus proving it is safe to be applied on the human body, as visible light could be used to excite the nanoparticles. In comparison to previous studies, the carbon cotton dots synthesized have excitation wavelengths around ultraviolet region or UV region, which is between 10 nanometers to 400 nanometers. Therefore, it may constrain the practical usage, especially on human bodies, because UV light is required to excite the nanoparticles. So this table shows a summary of the previous studies mentioned. As seen here, most studies exhibit excitation peak within the UV range. Next, so for the quantum yield, pure lemon juice exhibits external quantum efficiency of 0.223%. On the other hand, lemon onion mixture shows increased external quantum efficiency. This may due to the addition of onion juice to lemon juice, thus increasing the polarity of the solution. At optimal ratio, the efficiency was increased by 6 times that of pure lemon juice. So according to Lakowicz, the higher the polarity, the lower the energy is required for emission. Thus, higher emission could be observed from the sample. So next, this bar chart shows the external quantum efficiency of all samples based on lemon-onion ratio. So it shows that the ratio of 8:2 is the optimal ratio, and any increase or decrease of lemon ratio would decrease the external quantum yield efficiency. Furthermore, for infrared spectra, there are 3 peaks found: fluorides, amides, and hydroxyls. So therefore, it shows a successful unification of amino groups and hydroxyl, as well as minor fluorides and ether on both pure lemon juice and lemon onion mixture carbon content dot surfaces. So the strong peak for hydroxyl proves that the carbon content dots have high solubility and polarity and are suitable to be applied to feasible products such as soaps or nanomedicine. Then, as comparison, a study by Montefiore et al. Was used due to it also uses lemon-onion mixture as the sample. In the aspect of quantum yield percentage, it shows that the previous study it shows that previous study exhibits higher quantum yield percentage than of my study. While in the aspect of solvents, the previous study uses ethanol, while in this study, no solvents were used. Although the low quantum yield percentage, my sample is all natural with no chemicals used. When used at body or food, less solvents is better. So for my sample, safety first, quality is second. So in conclusion, the carbon content dots are synthesized successfully using lemon juice under hydrothermal method at 120 degrees Celsius for 3 hours. So the quantum yield percentage is successfully enhanced by mixing onion juice, which is approximately 6 times higher at optimal ratio. So then the relationship between the lemon-onion ratio and quantum yield percentage is also found. So when lemon ratio increase or decrease from the optimal ratio, the quantum yield percentage decreases. And finally, quantum yield of synthesized carbon content dots in this study is lower than the previous studies. However, the ones produced in this study is more consumer-friendly as no chemicals are used in the process. So these are the limitations of the studies and some recommendations. So firstly, there are differences in types of onions, such as red, white, and yellow onions. So this may cause a difference in results. So as a recommendation for future works, a quantum yield test comparing different types of onion could be done. Moreover, large quantity of lemon juice is required to extract a little amount of quantum yield. So synthesis could be assisted by using microwave pyrolysis method. Moreover, this study is only done at a lab scale. If possible, the study could potentially try at a large or practical scale, such as nanomedicines and bioimaging. And finally, this is the list of my reference for this presentation. And that's all for my presentation. Thank you for listening, and I'm open for Q&A. Thank you.
Okay, thank you, Mr. Ko Johans. So if anyone has any question, I'm sure Mr. Ko Johan would be pleased to answer them. So any question from the audience? Okay, I have one question.
Yes.
After you extract these carbon quantum dots, did you try to apply in any application?
Because after this experiment, the MCO the lockdown happened, so I haven't did any application purposes, but I am now currently starting a study using this carbon content dots to be applied in paper-based sensors. So I think I'll be starting on simulation for now because of the lockdown, but I'll try to do it when the lockdown ended, and I'll try to do it on hand. But for now, I'm currently studying on the simulation part of the this application.
Okay, thank you. Thank you, Mr. Ko Johans.
Okay.
So can we go back to Dr. Chong Soo Sin? Are you still here?
Sorry, I'm so sorry about that.
It's okay. So can you start to present now?
Sure.
Okay.
So let me share my screen again. I'm so sorry for everyone. So since I'm the last, so okay, let me share my screen with you all. Okay, can you see this time?
Presenting now. Okay, now it's okay.
I'm so sorry, you guys. So actually, just now, my colleague, Mr. Ko, already present the biomass derived quantum dot. Actually, what we are going to do for coming now actually is a sensor base. So since due to the lockdown in Malaysia, we haven't have a really hands-on experience, what we call that, a real application of that. Therefore, I try to apply his result and apply in my sensor, and then simulate the interfacial behavior of the fiber optic sensor for soil moisture monitoring. So this time we come here is seek for collaboration. So if someone has interest on that, would like to collaborate with us, then we can have a further discussion later. So you may drop me an email. This is my email. So or drop Mr. Ko an email also can. So okay, the result is not much. Just would like to share you all our idea. Okay, so the agriculture in Malaysia is still dominated by smallholder with an aging farmer population. So therefore, mostly they using is a very traditional way. Even they don't have the monitoring system, they normally use based on their experience. So therefore, they will rely on manpower. Of course, this is costly as well. So especially for the soil moisture monitoring. Okay, so in Malaysia, okay, we would like to encourage, especially the government would like to encourage people to involve in agriculture. So in order to in line with the Industrial Revolution 4.0 and Sustainable Development Goal 2030 to further modernize the agro-food sector. So it will be relevant and support the aspiration of the Shared Prosperity Vision 2030. So this caused me to think about what fiber optic sensor can do here. So in this sensor, I try to simulate it. Okay, this is side polish sensor, and then I will simulate the code with a quantum dot, as Mr. Ko presented just now, and then try to simulate the interfacial behavior between the coating layer and the soil's moisture. So in order, because in the soil, there are many parameters that could affect the signal. So let's say moisture could affect pH, pesticide, or others, what we call that, is other factors also could cause the signal change. In order to obtain more sensitive and more accurate result, therefore, I decide to coat a layer. But we have lack of knowledge, okay, lack of knowledge. What is the interfacial behavior between this coating and the soil moisture? So therefore, I conduct some simulation of it. So this is the coating material. So using the fruit.
Sorry, Doctor. We still at the first slide?
We're still in the first slide.
Okay.
So how about this one?
Okay, now we can see your second slide.
Okay, now go to the third one actually. I'm sorry about that. So we got in this simulation study, we will apply this fruit waste and then carbonize it, become a carbon-based quantum dot. Because carbon-based quantum dot normally they are toxic. So if we are using biomass derived, this is we have no concern in the safety issue if we apply in agriculture sector, because agriculture is, we would like to generate food. So if safety is one of the concern, one of the issue, so this is not good. I think this is not good enough. Therefore, in this simulation, it could be the quantum dot layer with the fiber optics side polish sensor in order to detect the soil's moisture. So this is how does the sensor work. Actually, this sensor is not a really new idea. So this is the LED light. We will coat the sensor with a layer of the quantum dot, and then this is considered as N2. After that, N3 is the core, N4 is the cladding. And then when the source moisture from the ambient environment, it will be absorbed by the quantum dot layer. So when the quantum dot layer absorbs some moisture from the soil, the refractive index will change. Of course, the light refract and reflect in the sensor will change as well. And it could affect the final intensity that you collect at the end of the sensor. So because as mentioned at the beginning, we would like to fabricate a low-cost sensor which is affordable to everyone. So therefore, we didn't use OSA. We may use just simple light intensity for the detection only. So this is the idea. So in the simulation process, because we would like to know whether this idea is workable or not for the source moisture monitoring. So therefore, I'm using the multi-physics console to generate a module. Okay, so at the first one, I generate the geometry. Okay, plot the geometry in the 2D form, and then I'm using the mass study. Okay, and this is the final one. This is the mood analysis. In this mood analysis, you can see that, okay, of course, in the middle one is the core. So the signal is the highest. This is the correct. And then since we have the side polish, so there's some wave already leaking. So in order to interact with the coding layer, and the coding layer which will interact with the source moisture as well. So this is just a very brief simulation, okay, in order to know that this idea is workable, and our quantum dot layer also workable to detect the source moisture. So if you have any interest to provide to us, or you would like to share with us, feel free to drop me an email as below. Okay, so thanks for watching. I apologize for the internet issue here. So thank you very much. So any question, feel free to ask me now. Thank you.
Okay, thank you, Dr. Chong Susin. So anyone have any question to ask? You can ask now. So I think there is no question for Dr. Chong.
Yeah.
But I have one question. So now we just make the simulation, right? So did you consider the distance between the sample and your side polish fiber?
You mean the sample?
Yes, the interaction between your sample and side polish fiber. How deep is your side polish fiber? Did you calculate determine the minimum?
Minimum of, you means the morphology?
Not the morphology. I think to allow the interaction happen between your sample and the light.
Not yet. We have. I haven't do the simulation yet, because especially as Doctor mentioned just now, especially the coating thickness. This is very crucial on the fiber, and the types of the fiber also one of the reason. So to change the effectiveness of this sensor, because if we choose for the silica, so because this simulation is based on silica, so but in the real practical application, silica is not really good for agriculture use, especially side polish, because in agriculture use they are more robust. They need something more robust. In silica, actually they are more fragile, easy to break. So I will try in the next round using the plastic, maybe more feasible. Okay, and try to simulate the thickness of the coating and the morphology as well. And then another thing is in the next study, we will study the cross sensitivity as well. So cross sensitivity, which means include the pH, include the temperature. sometimes increase the pressure as well, because if we bury it under the ground to detect the soil's moisture, just in case if someone gives some the pressure on the top of the ground, so it will affect the result or not. So every signal actually we need to do some some kind of extraction. So we need to eliminate those in order we just get the signal for the soil's moisture. So it seems like complicated. Actually, it is not really. It's just simple. It's not really too complicated. So this is the idea.
Okay.
Okay.
I'm interested in this project actually, so I will contact you later.
Yeah, thank you.
Okay, thank you, Dr. Chong Soon Sing, for this informative and interesting talk. So I think this we come to the end part of our presentation now. So we would like to thank all the presenters for the informative and interesting talk, and also to the audience and our keynote speaker. We appreciate you taking time off your busy schedule to join us today. So thank you for your attention. See you tomorrow for the second day of this conference. Thank you.